All right. Hi, everyone. It's wonderful to have you all here. I'm extremely excited to be participating in the Transform virtual conference this year. And I'm thrilled to be sharing with you some of the work that our team has been doing on building up SimPEG, a software package for simulation and parameter estimation in geophysics. And so today we'll be walking through a few examples, and I'm grateful you're all here. So you'll see at the bottom of the screen there's two links. So this first link here, this is where you can go to access the GitHub repository that contains the notebooks and materials for this course. And then there's also a link for the Slack channel, and it's this hashtag here, this channel here. So T20 Tuesday SimPEG is where you can go to ask questions, and there's a whole team of folks there who are willing to help answer. So if you run into any issues, please feel free to post there. So before we get going, I wanted to say a big thank you to the organizers. This has been a really exciting event to be a part of. I think it's amazing that we can connect with folks from all around the world and be sharing some interesting work on the geosciences. But in particular, I want to thank Matt and Brendan, who have been coordinating with me and created this opportunity to be presenting. So again, here's the link for the resources, and this will be posted in a few different places, and it's also available in the Slack channel. Perfect. So let's start by considering what type of experiments are we going to be looking at, and what is the setup of our problem that we're considering. So here, what we're going to be looking at is geophysical simulations and inversions. And so we've got the Earth, which is characterized by some physical properties, so maybe electrical resistivity. And what we're going to do is we're going to input some source energy and measure some data that are sensitive to those variations in physical properties. And then the goal in an inversion is to take those data and then try and obtain some information about the subsurface physical properties. And so there's a whole bunch of different physical properties that we could consider. We can consider things like density, magnetic susceptibility, electrical properties like resistivity or chargeability or permittivity, as well as elastic properties. So in this tutorial, we're going to focus in on electrical resistivity and chargeability. And but a lot of the fundamental principles that we'll be exploring are going to be the same for all of these different properties. So let's start by considering electrical resistivity or conductivity. And so what is that? It's a measure of how easily current can pass through a material. So there's two different symbols we often use to characterize this. So sigma, we refer to as electrical conductivity, which is in units of Siemens per meter. And then there's resistivity, which is its inverse, so 1 over sigma, and that's in units of ohm meters. And so we'll end up using these somewhat interchangeably. I will do my best to stick with resistivity as the primary property that we'll be speaking about today. But if I do say conductivity, just know that it's the inverse of resistivity. And so electrical resistivity, it depends on quite a number of factors. And when we're looking at earth materials, it's things like mineralogy, the porosity and permeability, and maybe the nature of the pore fluid. So if we have a saline fluid versus a more fresh fluid, that's going to change the resistivity. So here on the right, we've just got a sample of a few different materials that we might encounter in geologic settings. And you can see that resistivity, it varies over several orders of magnitude. So we can go from anything like a massive sulfide, which is quite conductive, down to igneous rocks, which are very resistive, and anything in between. The other physical property we'll consider is called chargeability. And so what this is it's the tendency for a material to act like a capacitor and build up charges. And so the actual physical mechanisms of this are they're involved, and there's active research going on and really understanding the fundamental principles of what's going on. But conceptually, there's two models that are quite constructive to use as sort of a mental understanding of what's going on. So the first that we'll consider is called membrane polarization. And so what this is if we have a pore throat that's narrow and narrow enough that we're not going to get ions in the fluid going through there, if we apply an electric field, we'll get a buildup of charges because they can't simply pass through there. And so that gives us a polarization, and that's what we're sensitive to when we talk about a material being chargeable. The other mechanism is called electrode polarization. So if instead of having just a narrow pore throat, we actually have some sort of metallic mineral in that pore throat, then what happens when we apply an electric field? We polarize that metallic particle, and then that's going to attract charges and ions in the fluid on either side. And so again, that gives us this polarization. And when we talk about Earth materials, so some of the materials that tend to be more chargeable are materials like pyrite or sulfides. And so those are things that we're quite sensitive to when we do induced polarization surveys, which are sensitive to chargeability. And we'll talk about those in a moment. Okay, so what's the basic geophysical experiment that we consider when we're looking for conductive or chargeable materials? So what we're going to do is we're going to consider a mineral exploration example. And so this is based on a deposit called the Oilera deposit, where we've got a conductive region of mineralization, and it's capped by a resistive unit here. So what we're going to do is we have current electrodes that we're going to connect to the ground. And what we're going to do is we're going to inject current through those. And then our receivers are going to be these potential electrodes, and they're going to measure a potential difference. So first things first, we turn on our electrodes and we set up the current. So the currents in the Earth, they're going to preferentially flow through conductive units. So if here our mineralized units are more conductive than the surrounding host rock, we're going to get a preferential flow of currents through those units. And with that, we then get charges that build up at interfaces. So when we transition from a conductor to a resistor or a resistor to a conductor, we get a buildup of charges at those interfaces. And then as a result, those charges create electric potentials. And that is then what we measure at the surface of the Earth. So by measuring potentials at the surface of the Earth, we can get some information about where charges are building up, and that is connected to then the resistivity of the subsurface. So that first part that I walked through is typical of what we would call a DC resistivity experiment, a direct current resistivity experiment. So we turn on the currents, we turn on our transmitter, and those create currents that preferentially flow through conductors or around resistors, and then we get the charge buildup. And in a DC experiment, that happens all instantaneously, is that we get this buildup of charges instantaneously. When we talk about induced polarization, that charge buildup occurs over time. And so in one experiment, we can actually get information about both of these physical properties. So here, when we turn on a transmitter, we instantaneously get a potential difference. And then this slow buildup is the charging up or polarizing of materials. And then when we shut that off, the DC component goes away right away. And then this decay is related to the chargeability of those materials. And so by looking at both the instantaneous response as well as these decays, we can then get information both about the resistivity of the subsurface and the chargeability of the subsurface. So the example that we're going to look at today is in mineral exploration. So DC and IP have been recognized as potentially useful for mineral exploration since the 1950s. But it wasn't really until the 90s that we started to have the algorithms as well as the computational power to actually start working with these data and in order to recover 2D images of the subsurface. And so why this is important is we actually want to try and understand and build up geologic images and geologic interpretations from our geophysical data. So the specific deposit that we're going to look at is called the Century deposit. So it is near the Mount Isa region in Queensland, Australia. And so these are the data that we're going to be considering. It is a zinc, lead, silver deposit. And this was really one of the early successes of DC resistivity and IP in mineral exploration. As we'll see in the examples coming up, IP was really influential in helping understand the extent of mineralization in this region. And here, there's a paper that we'll be referencing extensively, this Mutton 2000 paper. This is linked here, and I believe it should also be linked in the main resources that we shared on the GitHub repository. Okay, so let's start now by looking at what's the geology and what are the physical properties that we're going to be looking for. So the mineralized sequence that we're interested in, it's about 40 meters thick. And it's within these black carbonaceous shales. So if we look here at this diagram, it's these 4 units that are tracking basically right along here in these carbonaceous shales. And so the 2 physical properties, what we're going to be getting from both of these is the resistivity gives us structural information. So here we see we've got some sandstones and siltstones and shales. And so those might be more conductive units where we have a higher porosity, for example. And so we can see a fault here where we've got a discontinuity between where these units are in the subsurface. And so that's going to be the first step that we're going to work with, is working with these resistivity data. And then the chargeability is actually associated with the mineralized units. And so in this case, there's sulfides. And so that's something that we know we can be sensitive to with an IP experiment. So this plot here, what it's showing you is a bit of a summary of what I just mentioned. So here we've got each of the different geologic units mentioned. So these are just the short names here. So if we look, for example, the CLS is the Cambrian limestone. And then units 1, 2, 3, and 4 are the mineralized units. So the black curve here is resistivity. So we can see that the Cambrian limestone here is very resistive. And so that's sitting up here. Some of these other units are a bit more conductive. So where we've got the hanging wall sandstone, for example, this guy, or the siltstone shale are both on the more conductive side of things. So that's conductive because, again, it's a low resistivity. But then here, if we look at our mineralized units, they're sort of in the middle. So it's not necessarily that DC resistivity is going to be diagnostic for these units, but they're going to help us build up the geologic picture. And then in this case, we can see when we look at the chargeability, which is the bars here, and it's on this axis here, these 4 mineralized units are much higher than the others. And so this gives us some confidence that chargeability is indeed going to be something that is constructive and will hopefully help us be able to delineate these units. Okay, so now we're going to look at our data. So there, as we mentioned, we can collect both DC and IP data from the same survey. So this is one line that we're going to focus in on. And this was the line of data that's originally published in that paper. So we're going to be able to go ahead and compare the results that we generate with SimPEG to results that were published about 20 years ago at this point. So what we're showing here is we've got what's called a pseudo section of data. And so we'll walk through in the code how this is actually built up and how to sort of conceptualize where a datum is plotted given the source and receiver locations. But basically, it's a way to image and plot your data where we can say that data that are closer to the top are going to be probably more sensitive to the near surface, whereas data that are closer to the bottom are going to be a bit sensitive to deeper structures. And so visually, sort of looking at it vertically, that's where you can understand what's going on there. Sorry, I am going to close my window because there's a lawnmower outside. Sorry about that. Okay, so the top plot, what we're looking at, what we've plotted here is apparent resistivity. And so this is just one way of visualizing our data. We've translated electric potentials into an apparent resistivity. And again, in the code, we'll walk through what that means. These are not true resistivity values, so you shouldn't be interpreting this as geologic units, but it's just a way to visualize and understand and also QC the data. And then similarly here, we can plot up the IP data. And so looking at these, we can see there's something interesting going on here. We've got some higher chargeability here. So there's something interesting happening in our data. All right, so now we've got these data. Our goal is to invert them to now obtain physical property models giving us the resistivity using the DC data and the chargeability from the IP data. So what are we up against when we talk about inverting data? So we've got our data and hopefully some uncertainty estimates that gives us a sense of how much we trust those data. We also have our governing equations. So we know for DC resistivity, we're starting with the static Maxwell's equations. And then we might also know something about the geology of the area. So we might know what rock units we're expecting to see. Maybe we have some well logs that give us some information about the physical properties of the rocks that we're going to be encountering. So these are all of our inputs. And then what we want to get out at the end of the day is a model. And so in order to be able to do that, we need to both be able to forward simulate our data. So meaning that given a model of the Earth, we should be able to predict what data we should be measuring. And so for this, we're going to need to be able to break up the Earth. So write down some sort of discretization, and then go ahead and solve those equations. And then in the inversion, what we're going to do is now we're going to set up an optimization problem where we're going to try and fit those data. So we want the data that we're predicting to match the data that we observe. And in order to have that problem be tractable, we're going to impose some regularization. And we'll walk through what that means. So SimPEG is what we've developed as a mechanism of solving these types of problems. And so right now we've got utilities and functionality for simulating and inverting quite a number of data types. So gravity, magnetics, DC resistivity, IP, electromagnetics, as well as fluid flow. And so all of these problems can fit into a framework like this. So as I mentioned, there's two pieces that we need. We need to be able to predict data. So we're going to break up the world into blocks, like Lego blocks, and simulate equations over them. So in this case, we simulate the DC resistivity equations, which look like this. And I'll walk through these. And then, as I mentioned before, we then want to run an optimization where we're now going to try and estimate a model. So we set up an objective function where we have one part where we want to fit our data, and then one part where we use a regularization where we can impose some geologic constraints, and also perhaps ask for a smooth model, so that we actually can recover something that's geologically interpretable. And then we might have things like bound constraints. So if we know, for example, resistivity should always be greater than 0, we can't have negative resistivities, then we might want to impose that. So for DC resistivity, here's the equations we're going to be solving. And so this derivation is just to get you connected with the equations we're working with. So we start from the electrostatic Maxwell's equations, where here the E is the electric field. And because its curl is 0, that means we can represent it as the gradient of a potential. And so here we're going to use the symbol phi as the description for electric potentials. J is our current density. And so in this case, this is basically telling us a bit about conservation of charge, is that the divergence of J should be the negative of our source currents. And so our source currents, if they're point electrodes, so if we just have 2 electrodes in the ground, we can think of those basically as delta functions. We've got one place where we're injecting current and one negative electrode where the current returns to. And then finally, we have Ohm's law that relates the current density, which is a flux, to the electric field through the resistivity or the conductivity. And so by piecing all of these together, we get our governing partial differential equation. So, So we take the divergence of 1 over rho times the gradient of phi is some sort of source term. So that's what we solve in the DC resistivity equations. For induced polarization, we adopt a linear model for chargeability, or for IP. And so what we're going to do is we're going to linearize about the resistivity or conductivity. And so here we use the symbol eta to refer to the chargeability. And what its effect does is if we increase eta, we increase electrical resistivity. And so what we can do if we linearize the resistivity, is we can then actually write out a linear model for what an IP datum looks like. And this is true here for apparent chargeability data, which is what we're going to be working with for the Century deposit. And so here, those sensitivities, this linear portion, is just the sensitivities from the DC problem. So what that means is if we want to invert IP data, we first have to invert DC data in order to get those sensitivities, and then we can go ahead and invert or simulate IP data. So here, where our governing equations for IP are just a linear set of equations. And so the linear equations are similar to what you would encounter in potential fields problems as well. So if you want to work with gravity data or magnetics data, in those cases, we're often working with a linear set of equations too. So as I mentioned, if we're going to work with IP data, it's a two-step process. So step one, we invert the DC data to get out a resistivity model. That model and those sensitivities are then used to do step two, which is the inversion of the IP data. So we use those sensitivities then to perform this inversion and get a chargeability model. So this is what we're going to be doing in the first notebook. And these results here that we're looking at are from the UBC inversion that was run 20 years ago. So let's actually walk through how were those results originally obtained. So the image that you will see on the right is published in the Mutton paper. So this was the original inversion and original image of the IP data on the line that we'll be working with. So you'll see this number quite a bit as we go through the notebooks. That's the line that we're going to work with. There's 27 sources on this line and 151 data in total. These data were originally inverted with the DC IP inversion codes developed by UBC GIF in 1992. And the mesh that was used to run this 2D inversion had about 1,000 cells. And at the time, it was run on a large Sun workstation. It took about an hour per iteration. So in order to obtain this image here, that was about a day's worth of computation. And so we're going to see what we can do 20 years later and in Python. But before we get there, let's take a look and actually see what we can understand from the geology if we're looking at these inversion results. Okay, so the first piece we're going to look at is the DC inversion result. So here, what we have plotted, what the color indicates is resistivity. So reds here are more conductive, so it's a lower resistivity, and blues are more resistive. And so if we want to try and interpret this image in the context of the geology that we're seeing, we relate the geophysical image to the geology through the physical properties. So here we're looking at resistivity. So let's come back to the resistivity measurements of the geologic units at Century. So in this case, we see we've got some resistors. So we've got some near surface resistors here and out here. And looking at our resistivity plot and physical property values, it's quite likely, especially at the near surface, that these resistive units that we're seeing are these carbonaceous, or sorry, the Cambrian limestone. So you can see here that tracks out near the top. And then as we have this fault here, it looks like this unit does go deeper. So this resistivity image seems to be agreeing fairly well with what we expect to see for the Cambrian limestone. Then we can also see a couple conductive features. So we've got a bit of a conductor here and maybe something up here. And if we look both at the physical property values as well as our geologic section, it would make sense if these correlate then with what we're seeing for the hanging wall sandstone. So this guy here, which is here on this side. And then if we look in the center region, it's corresponding to this sedimentary segment here. And so these seem to be aligning fairly well. So these lines are showing these faults there too. So that gives us some confidence that we can interpret this image in terms of the geology. It's also encouraging to see that here, where we've got this conductive unit, there is a bit of a disruption and a discontinuity where we see the fault. And And similarly here, this is this resistor that's starting to come in doesn't necessarily exist on either side. So we're seeing some structural information from the resistivity image, as well as potentially being able to understand where some of these geologic units are. All right, so now to the chargeability. So we use that resistivity model now to run the IP inversion. So we're working with the same line of data, but now we're looking at chargeability. So we have blue being low chargeability. So that means that these rocks tend not to support a buildup of charges. And then where we've got higher chargeability is red. And so those units tend to support the buildup of charges. And so what's really encouraging to see here is where we're expecting to see these mineralized zones, which are sketched out here and here, is we are seeing a strong chargeable response. And so these align well with what is observed from drilling. And so this image where we're seeing basically being able to image the extent of the mineralized region, this was an extremely compelling result, because instead of having to drill and continually use a drilling program to delineate the extent of mineralization, instead of that being the only tool that you have, we now actually have an image from data completely collected at the surface that we can use to try and estimate the extent of the mineralized zones. So this was a real early success story of how images obtained from geophysics can really aid the understanding of geologic structures and aid decision-making in mineral exploration. So in summary, we started from DCIP data collected over a century. We looked at the UBC inversion results using the DC code. We were able to understand perhaps where some of these sedimentary units lie, and so get some geologic understanding, as well as observing discontinuities in structures that align well with the faults that we see. This information was then used to obtain an IP, to run the IP inversion. And here we're able to image the extent of the mineralized zones from the IP data. So these are the data that we'll be working with in the first notebook that we're going to open up. So our goal is going to be to invert the DCIP data from Century using SimPEG. And so the first question we want to ask is, can we replicate these results from 20 years ago using a different code and perhaps our own different choices and parameters? In the next notebook, we'll go through and we'll explore some of the fundamentals of the physics of DC resistivity. And this will hopefully give you some ideas about how you can set up your own forward modeling with SimPEG, and also explore aspects of the physics like the currents, charges, electric fields, and potentials. And so if you're looking at survey design type problems, hopefully what you learn here will extend to other methods that you might be interested in. And then in the last notebook, we're going to go ahead and we'll look at some of the important choices in the inversion. There's lots of knobs and parameters that you can tune. And so we built up some ways to go ahead and explore those and hopefully build some intuition of what they all do. One thing I'll note is that in this case, with the layout of the notebooks, there's a lot of code. So we tried to be very explicit and walk through step by step. Some of the things we're going to probably gloss over a bit today, but we'll be very active in Slack and happy to answer questions. My goal in doing this is really to first give some ideas as to really how the SimPEG framework works. And so instead of hiding things in utility functions and things like that, we're going to really work through all of the details so that if you have your own data file that you want to get loaded into SimPEG, and we maybe don't have a utility for that, walking through this will hopefully give you the conceptual model of how you would do that for your own data. Here's a bit of an optimistic schedule, potentially. So I say that because I was only planning for 20 minutes for this talk, and we're already at 30, but that's all right. That's how tutorials go. So we'll set out a schedule and we will see if we stick to it. But either way, here's the plan. So we'll start with notebook 1, and we'll invert the DC and IP data from Century. And throughout, we'll be highlighting aspects of the SimPEG framework. So this should give you an overall tour of how to use SimPEG to invert field data. We'll take a bit of a break after that, and then we'll have some time for a bit of Q&A. And so again, please feel free to drop questions in Slack. I already see that there's quite a bit of activity there. I know some folks are potentially running into some challenges getting up and running on the code. And so if you do run into any issues today and want to just follow along, feel free to also use the binder link. So that should work and run online. And that'll allow you to follow along in real time. And then afterwards, we can always give you a hand with getting SimPEG and the notebooks up and running on your computer. Yeah, so if you have questions, both technical or conceptual, feel free to please drop those in Slack. There's a number of folks who are helping out, helping answer questions, and they will flag questions and send those to me, and we can answer them after the break. Then Notebook 2, we're going to be diving into forward simulation, exploring some aspects of how to set up a forward simulation and what sorts of choices matter in order to get accurate results. And then finally, in Notebook 3, we will focus in on inversion. And then ideally, we will end with a little bit of Q&A. I also wanted to include just a few links to some resources. I know that we've got a broad audience here, and so some folks might be, DC resistivities in their wheelhouse, and for other folks, these might be newer concepts. And so here's a suite of resources on geophysics and inversions. So we've got Geophysics for Practicing Geoscientists. This is a textbook we've used in a number of undergraduate courses, and is meant to be an introductory tour to a whole suite of geophysical methods. EM-Geosci is a bit more of an advanced resource on electromagnetic methods in geophysics. And then with both of those, we've got some lectures recorded. And then specifically with respect to SimPEG, here's a few links for getting you up and running. So we've got documentation. Discourse is a good place to go and ask questions, as well as the SimPEG Slack. I wanted to give a big shout out to the SimPEG team, and specifically the folks who are jumping in today and helping answer questions. Here's everyone's Slack, the swung Slack handles. So if you're running into issues, please feel free to tag any of us directly. I also want to thank Yagua Lee and Doug Oldenburg for both getting us set up and running with these data and providing some context background on Sentry and going through and giving us a review on these notebooks. All right, so before we transition, I'll just keep this up for a moment so that folks can copy the link if you haven't already. But we'll be starting here is where the GitHub repository is for the content. And then again, as I mentioned, Slack is where you should come to ask questions. All right, so what we're going to do now is we're going to go ahead and go over now to the GitHub repository. So I want to show you what that looks like. And if folks have not already downloaded the code and want to, this would be a good time. So if you follow that link, it will take you here to the SimPEG organization, to the Transform 2020 tutorials. So we've got the data here, there's 3 notebooks, and then the README contains all of the information that you need. So the live stream, which is happening right now. So I guess you're already successful if you're watching this. And then the link to the slides that I just used is right here. And then the Conda environment you'll be using is this guy. So if you haven't gotten set up and running, go ahead and take a look here now at the usage section. So in step 1, you need to get Python. Hopefully you've already done that. And then here we've got steps to git clone and create the Conda environment for this repository. So please go ahead and follow these steps. If you run into any issues, ping on Slack. If you do run into issues and you want to follow along live, just use the binder link here, and this will bring you to a web interface where you can run the notebooks. Okay, so once you've gotten up and running, we're going to start by taking a look at the first notebook. So the inversion of DC and IP data at the Sentry deposit. Perfect. So this is the line of data that we're working with. So we saw this map already. So this 46800 east line is the one we're working with. Again, here's our geologic section. and the result that we're aiming for. So can we replicate this result and maybe update the color bar? I can hear Swung folks cringing silently on the other side by looking at a jet color bar. I've seen many great posts on that. All right, so the first step we're going to do is we're going to import our dependencies. I'm just going to make this bigger to make sure folks can see it all right. So I put in links here to some of the core tools that we're using. So if you're not familiar with NumPy, Matplotlib, or IPy widgets, there's links to the documentation on each of these. These are pretty standard Python libraries. And then there's some things that we're going to be importing that are specific to the SimPEG ecosystem. So this package called Discretize, what that's going to give us is all of the meshing capabilities as well as the differential operators. So when we're going to build up a partial differential equation, Discretize is what will give us the gradients, divergence, etc. The PyMat solver library gives us wrappers on fast linear solvers. So here we're going to try and use Paradiso as our solver, which is much faster than any of the basic solvers like LU. And then SimPEG is where we're going to be spending most of our time. And so SimPEG, the original acronym, stands for Simulation and Parameter Estimation in Geophysics. So this is just core Python that we're importing. We'll import Discretize, PyMat solver, and then within SimPEG, so these now you're going to see throughout. And I'll explain step by step once we introduce them what each of these modules do. But we've got data, we've got mappings, things like the data misfit, regularization, optimization. So you'll see these come up throughout. And most of this is related to the inversion machinery. And then here, now we're looking at the physics that we're going to be working with. So we've got both direct current resistivity, which we import from the electromagnetics module of SimPEG, as well as induced polarization. Cool. All right. So we will import these guys. So if folks are not familiar with Jupyter, what I'm going to be doing when you see this transition from green to having a star in here and then down to the next cell, that is, I'm using Shift-Enter on my keyboard. And so if you're following along and want to be running the cells as we go, that's what I am doing. So here we're just going to set some bigger font sizes so we can see our plots. All right, so the first step we're going to be doing is actually loading up the data. So the survey collected at Century is what's called a dipole-dipole experiment. So what this is we've got our dipole source. So it's going to be 100 meters apart. We've got a positive electrode A and a negative electrode B, and that's our source. And there's a fixed separation between those. So these are going to be 100 meters apart in this survey. And then we've got our dipole receivers. So we call the positive one M and the negative one N. And that is what we measure a potential difference over. And so to probe different depths, what we do is we're just going to move and separate both the source electrodes and the receiver electrodes by different distances. And so basically the further apart that they are, the deeper that we should be imaging because we're looking at a larger volume of the Earth. So in this repository, we've got a directory called Century. And so what I'm going to do is we're just going to list that and see what's in there. So there's a few things that we don't need to worry about, dot files and stuff like that. The ones that we're focused on for this tutorial are the numbers and then where we've got a letter afterwards. And each of those is now, that contains the data for a specific line that was collected in the Century deposit. And the one we're going to focus in on is this guy. And so what I'm going to do is now just print what's in that directory. So there's a few different things in here. We've got some log files, some obs files, out files, etc. The ones that we're most concerned about are the obs files. Those are our observations. The rest of the files are actually related to the UBC inversion results. So these are things that we're going to be able to compare to. So these are archived inversion results. But the ones we're going to be working with in this tutorial are this one. So the POT stands for potential. So these are our DC resistivity data. And then this guy here, IP is our induced polarization data. So these are the two data files that we are going to be focused on. Okay, so now I'm going to just show you. Let's just open up the file and let's see what's in the file. So if we print out the contents of the file, the first thing we see is we've got some information up top. So this is just a comment. It's a bit of a description. It's a description of the data. The next line here is the number of sources. So we've got 27 sources in total. And then both of these are just flags. If it's a 1, it's a dipole for the source and for the receiver. So this is a dipole-dipole survey. All right, now we're actually going to look and see what the data are. So the way that this is structured is this so the first line after we know how many sources we've got is the location of the first source electrode. So this is the location, this is the A location, so the location of the positive electrode, source electrode, and this is the B location, so the location of the negative electrode. And you can see that they're 100 meters apart. This number here is then the number of receivers that are listening to that source or that are collecting data from that source. And then so the next two lines are then the location of those receivers. So this is the M location of receiver 1 and the N location of receiver 1. This is the measured potential. And then this is the assigned uncertainty. So these data, the uncertainties have already been assigned for us. In Notebook 3, we'll explore the case where if you have to assign your own uncertainties. But for this inversion, we'll just work with the uncertainties that were used in the UBC inversion. Okay, so this is what our file looks like. So now we actually need to get it into a useful form in Python. So what we're going to do here is we're going to write a simple function that is going to read those data in. And so within SimPEG, we have lots of utilities to read in data files and things like that. But here I wanted to do it from scratch so that you get a sense of how we can actually work with these data. So there's two things you can input. So we'll input the file name and then verbose. So in this case, I'm going to print some stuff so that we can just kind of make sure that we've read things in properly. And for now, we're just going to read it into a Python dictionary. So we're not doing anything with SimPEG yet. We're just going to read these data into a dictionary. That's going to contain the locations of all of the electrodes, the observed data, the standard deviations, and the number of sources. So here, this is just a function in NumPy that just reads the content into strings. So each line is then a NumPy array of a string with each new array being delimited by a new line. So basically, we're going to end up with an array where we've got however many lines there are in this file. That'll be that length of that array. We know that the first line is the first line after the comment line is the number of sources. So we grab that. If we're going to just print some information, we'll print that out. And then we'll initialize some storage for the source electrodes and locations of the data. So we know that there are 27 sources. So we'll just create that space directly for A and B. And then the rest we're going to use lists because we don't know from starting at the very top of the file how many M locations, for example, that we have. And then here I just have a little index where basically we're going to just keep track of which line we've read. So we'll loop over sources, and then for each source, we're going to read in its receivers, associated receivers and data. And then here we'll just print out some information to make sure that we've read things incorrectly. So that's all that this is doing, is we initialize space for the receiver electrodes that are associated with a given source, and same thing for the data. And then we just put all of that information into a dictionary. So let's run that. I said verbose is true so that we can kind of print some things out. So here we read in, we've got the right number of sources. For source 0, we got the A location, B location, and number of receivers. So we can make sure and sort of double check based on the data file that we are looking at if we've read things incorrectly. Yes, I will make my text a bit bigger here. Perfect. Folks, is that text size a bit better? I was getting some feedback there. Okay, so here, let's now actually take a look at what some of the information is in that dictionary. There we go. Okay, so we've got now, there are a number of entries in our dictionary. So our A location is a NumPy array, as we said before. Our M locations are a list, same thing as the N locations, standard deviations, and observed data. So let's just take a quick look at those. So our A locations, we got an array of all of our A locations. So this is the whole survey. We've got, it should be length 27. As we expected. So then let's also take a look and get a sense of now what our receivers look like, because these are a bit more involved. We know we've got 27 sources in total, but the number of receivers and the number of data associated with each source is a bit different. So the way that we're going to track that is now basically, so we see that, for example, the M locations is a list. So it's a list of NumPy arrays. And so the first array is the M locations associated with the first source. And so here, when we had 2 receivers for the first source, we should have 2 M locations associated with that first entry. And this is the same organization we use for the observed data, for example. So same idea here. So we get 2 datums associated with that first source. So you can sort of see there's this hierarchy here now where we've got sources first, and then under the sources, we know how many receivers and how many data are associated with each of those. Okay, and so this is basically going to be mimicked in how we set up things in SimPEG. So far we haven't actually touched SimPEG. We've basically been in pure Python. So now we get to the SimPEG part. So the survey object in SimPEG is going to be what keeps track of our geometry of the sources and receivers in our survey. So similar to the way we saw that file was structured, each source is going to take a receiver list, which knows about the different receivers that are listening to or associated with that source. So just as a simple example here, if we take the first 2 datums that we're going to get from our file, we know we've got M locations. So we have 2 M locations and 2 N locations. And it's a dipole. So we can create a dipole receiver. So you'll notice here that I'm not creating 2 receivers. I'm only creating one receiver object. And that's because it's all of the same type. If you, for example, had a survey where maybe you had dipole and poles, then in this case, we would need to add the pole receivers to our receiver list. But if you only have dipoles, then we only need to create one receiver object associated with those multiple locations. Another thing to note is that in SimPEG, we use column major ordering. So that's the same idea as Fortran ordering. So here, when we talk about the X locations, those are going to be in the first column. We're going to be doing a 2D simulation and a 2D inversion. So these need to be located in 2D space. So we're not going to consider topography. So these zeros here are the Z locations, and those are just going to be on the surface of the Earth. If you did have topography, for example, then you would input those guys. You'd input the correct locations here. Okay, so that gives us our first receiver. And now we want to create a source. So our source also has a location. And now a source has a single location. And so we're just going to put in the A electrode, so we know where it is along line. And then again, we're not using topography, so it'll be at the surface. So we tell it where our A location is, where our B location is. And then we can go ahead and construct a source object. So it is a dipole source with an A location, a B location, and a receiver list. And so very much similar to how we structured that dictionary, that's how we're going to structure our survey in SimPEG. And then the survey object at the end of the day is then just contains a source list. So we've done this for the first source, and then we would go ahead and repeat the process for all of the sources that we've got in our survey. So now we're just going to implement that in code. So we initialize an empty source list, and now we're going to just loop over the number of sources that we had, construct the receiver objects. So see here, we're going to grab those M locations for each of the sources. So this For the first entry, it'll be length 2. For others, it could be longer. Same thing for the end locations. We'll construct our receiver object, construct the source, which has its location and the receiver list, and then we'll return that source list. So here, if we then go ahead and look, for example, at the length of the source list, it's 27. And if we look at a source object, so let's just say we've got source 1 is now source list at 0, we can look and we can see some of its properties. So source 1, it has a current, it's got a location, an A location, a B location, a number of data associated with it, so that should be 2. And then it also has its receiver list. Oops. It also has its receiver list, which in this case is that dipole receiver. So then once we have this source list, we can then go ahead and create the survey. And that is then just a container for that entire survey geometry. So if we look at some of the properties of the survey, for example, we can grab all the A locations, all the B locations. We can do things like we shouldn't do that there, sorry. Some of the API has changed, so I'm trying to be careful what I draw your attention to. So we can look at the number of data on the entire survey. So that's 151. So that's everything we need now to keep track of how were the data collected. So that's just the geometry, but the other thing that we need is we actually want to then keep track of the observed data and the standard deviations. And so within SimPEG, the way we do that is through this data object. So a data object takes a survey, which is that geometry we just created. It takes observed data. So in this case, the ordering of the observed data is exactly that sort of same wrapping that we just did for the survey. So the first datum should be associated with source 1 and receiver 1. The second one should be with source 1 and receiver 2, and then so on and so forth. So it's the exact same wrapping. So since this is in the same order as how we built up that dictionary, we can just stack the observed data and the standard deviations, and everything is in the right order. Okay, so now let's actually take a look at our data. And so as I mentioned before, we can plot data in pseudo-sections. So what I showed you in the slides was apparent resistivity, but that is a derivation basically from the voltages. So these are truly the voltages that are measured at the potential differences that are measured by our receivers. And so you can see it's kind of a little tricky to interpret. We've got some dark values, some large negative values near the surface, and it gets smaller as we go deeper. And so interpreting purely voltages or potential differences from a pseudo-section is a bit non-intuitive, because what you're basically looking at is we're getting information both about geology, so the physical properties of the subsurface, as well as survey geometry. Because if you've got a source really close to a receiver, that's going to give you a stronger potential difference. Whereas if you go further apart, those potential differences will be smaller. So we sort of have all of this information conglomerated into one. And so that's where we're going to go to apparent resistivity. But before we do that, I actually want to walk you through how these data are plotted. Because when I actually first plotted these up, this is a bit of an odd pseudo section. If you're used to looking at DC resistivity data, you often sort of see like a V, because we have more sensitivity and more data near the surface, and less spots as we go deeper, just based on the geometry. So I wasn't actually sure if this was correct or if I'd made a mistake somewhere. And so I built up a little app to actually go ahead and visualize how we're building up a pseudo section. So this is where I'm going to use the IPy widgets library. So I'm not necessarily going to go through this code. It's basically just a whole bunch of geometry of plotting where the sources and receiver locations are. And I think it's easier to actually just see if we visualize it. So here, the blue dots are the source location. So the dots are actually the positive and negative source electrodes. The X is the midpoint of those. And then the orange ones are our receiver locations. And again, the X's are the midpoints of those. And then so when we go ahead and we plot a datum on a pseudo section, what we're basically doing is we're drawing angles, straight lines from those, and plotting that in space. We're plotting that at a given depth. And so the deeper we are, the further apart they are. The shallower we are, the closer together the sources and receivers are. And so this first row are basically the closest point where the sources and receivers are closest together in the survey. And then as we go further apart, we go deeper. So let me just move this along so you can get a sense. So we've got source 0. That's what those data look like. If we move over, we added some sources there. So maybe when some of the processing was happening, maybe we actually cut out some data from these points or from those regions. So if we look here, this number n spacing is how we're basically choosing what depth it's plotted at. So this source and this receiver, they are the closest we're going to get to in this given survey. So the first source and the first receiver we plot by convention at n is 1. And then as we go further and deeper, the n spacing increases. So it's not a true depth, but it still is somewhat related to depth because as the source and receiver are further apart, we are seeing deeper. And so we can actually see when we go ahead and plot up all of these sources and receivers that it looks like our pseudo section is correct, but there was perhaps some processing that removed some of the data that would have given us that V shape that we're used to seeing. So the other thing I mentioned is that, looking just at potential differences isn't always intuitive. And so looking at apparent resistivity can give us a better way to sort of interpret and understand what our data are. And so what apparent resistivity basically does is we're trying to effectively remove some of the impacts of geometry. And so the way that we do that is we say, okay, what resistivity would we expect if the world were a half space? Because we can compute that analytically. And so this is the formula for that. And so you can see that G takes into account the geometry, and then delta V are our data. And so using this, we then go ahead and we can compute the apparent resistivity, which sort of accounts for some of that geometry. And so note that what we're doing here is we're basically saying, let's assume the world is a half space and see what resistivities we would get. So you can't interpret these as true resistivities because the world is not a half space. And there's variations in the physical properties and things like that. So this is not a true image of resistivity of the subsurface. There's still some elements of the physics in there, but it does give us a way to QC the data, see if there's any outliers and see if there's any interesting trends. And so this is the plot that I showed you earlier, where we're looking at the apparent resistivity pseudo section. So there's some regions, so out here, for example, we might expect that we should see more resistive materials when we run the inversion. Whereas in regions like this, where it's a bit darker, we're perhaps looking for something that might be a bit more conductive. And then two, this can be a good way to spot outliers. If you see a single point, for example, that has a very anomalous value, then that might raise some suspicions that maybe there's something that went wrong with that measurement. Another way to view data is to look at histograms. And this can be really useful in general, both for trying to assign uncertainties and estimate uncertainties, but also in more complicated surveys. So this was a nice 2D survey. But if you go out and you start creating larger 3D DC resistivity surveys, it can be non-trivial to figure out how to actually plot your data. And so in this case, we can plot up a histogram and see a nice distribution of our apparent resistivity values. So what we're going to use this for is to get an estimate of what should we be using for a background resistivity when we are running the inversion, is because that's something we need a starting resistivity where we start the inversion from, as well as a reference resistivity. And I'll show you where that comes in. So in this case, I chose to use the median. You could equally use, for example, the log mean. Sorry, let me add a cell so it doesn't jump. And we can see that those values aren't drastically different, but these are things that you can go ahead and explore. Another common choice would be to use the maximum likelihood, so we could use a value in here. And so all of these are valid things to look at, and so some of that really does come down to your geologic understanding of the setting, and yeah, and so you can try those out. But in this case, we're seeing that, a difference of about 10 ohm meters or so shouldn't drastically influence our results. Okay, so now we've got, oh, I see there's a question coming in. It might look timely. So with the contour F implemented within this function, how do you change the noise levels, i.e. increase? That's a good question. So in this case, we are, how do you, so you could use the pseudo section to get a sense of noise levels and things like that in your data. Often it's helpful to look at histograms, or in some cases, folks do repeat surveys where we switch out what the reverse the source electrodes with the receiver electrodes, and the measurements that you should get should be the same by reciprocity. So those types of things can give you a sense of what your noise levels are. And we'll explore that a bit more in the second notebook. So feel free to come back with another question if that doesn't answer what you were looking for. Okay, so we've got our data. We've got an estimate of what the background resistivity looks like. And so the next thing that we're gonna do is now set up the forward simulation machinery. So we know what our survey looks like. We know roughly, or we've got a guess of where we should be starting our model from. So now we need to simulate some physics. So these are the equations that I showed you in the slides. And so this is where discretize comes in, is we've got this PDE that we want to solve. And so in order to do that, what we're going to do is we're going to discretize the world, break it up into cubes, and assign basically locations for where each of these parameters lives on that mesh. So I've linked another tutorial that Rowan and I wrote a while back that goes through the derivation in a fair amount of detail as to how to actually derive the discrete version of the DC resistivity equations. I'm not going to go into detail here, but I'm just going to point out where the different things live, because this is important for understanding just physically where things put on a mesh. So in general, and basically everywhere throughout SimPEG, physical properties are discretized at cell centers. So you can think of basically the physical property filling the whole space in that cube, or for a 2D section in that square. In this case, we're going to use a nodal discretization of the DC resistivity equations. So we're going to put phi on nodes. You can also derive the DC equations with phi at cell centers, and that's what we do in this other tutorial. And so if you're curious, you can play around with both of these. They are both implemented in SimPEG. But for this specific discretization, we put phi on nodes, so potentials are on nodes. And then the electric field is then going to be on cell edges, so between nodes. And so one important thing when you discretize, and when we're actually solving PDEs on a mesh, is to know what our boundary conditions are. And so in this case, we use Neumann boundary conditions, which means that there's no flux of current through the boundary. And so in order for that to happen, what we need to do is make sure that when we design our mesh, that the boundaries extend sufficiently far away that there's no current that should be going through those boundaries. And in Notebook 2, we have a little app developed so that you can actually play around with some mesh design and see what happens when you either when you bring those cells, or when you don't extend the boundary far enough. A couple other things to consider. So I've got three main items that we'll consider at this point. And as I mentioned in the second notebook, you'll get a chance to explore them in detail. So the minimum cell size. And so this basically controls the resolution. And so what you need is, when we're simulating these electrodes, so we've got a source current going in one and current being picked up in another, we need to have enough cells in between them to actually capture the physics of that current moving. So if we only had one cell between them, that might not be enough to actually capture the physical phenomenon. And so we need to have potentially a few more. And so as a rule of thumb, we typically do about at least four cells per minimum electrode spacing. And again, this is something you can play with in that next notebook. So that gives us our minimum cell size. So that's decision one. The next one is the extent of the core domain. So basically, how big of a region in the mesh do we need to be using those small cells? So the horizontal dimension is pretty straightforward. We know where our electrodes are, where the furthest apart electrodes are. And so we usually use the extent of the survey and then perhaps add a few cells on either end. In the vertical direction, what we want to do is make sure that the core region extends to a depth which we're sensitive to variations in the physical properties. So as a rule of thumb, this is typically a fraction of the maximum source receiver separation. So maybe a factor of divide that by 3 should give you enough resolution at depth. And again, that's something you can play around with. And then finally, the last item we want to consider now is the extent of the full modeling domain. So we've got our core domain, which is really the region we care about imaging, but then we're going to add some padding to make sure that we satisfy those boundary conditions. So in this example, we'll use a tensor mesh. Sorry, I did not finish this sentence in the notebook, but basically what it is you can define each dimension by just specifying the cell width. So a tensor in each dimension is enough to define the entire mesh. If you're looking at larger domains, we have a tree mesh implemented. And so there's examples of that in the discretized documentation. So if you're doing a large 3D inversion, I'd recommend that you check that out. Okay, so here's the decision one that we were caring about is what's our minimum cell size. So in this case, we'll make it the same in X and Z. If you, for example, wanted higher resolution in Z, you can make these smaller, but we'll keep it the same, keep things simple. So we look at the minimum separation between our source electrodes. So we looked at the A locations and the B locations. And for this survey, it's 100 meters. And we'll do 4 cells between there. And so with that, we're then going to get a base mesh, or the core region of the mesh, with 25 meter by 25 meter cells. So that's going to be in the core region. And then we'll find our core domain in the X direction by just looking at where are our receivers and how far apart they are. So that's the extent, the lateral extent of the survey. Now to find the Z extent of the core domain, as I mentioned, we want to look at the midpoints and find the furthest midpoints. So here we find the midpoints of the A and B, and then the M and N, and then we find the separation and find the maximum of that. And then here we choose to divide it by 3. So you can explore in the next notebook some different ratios there and see what happens. So here we've got a maximum separation of 800 meters. And so our core domain in Z is going to go from -266 to 0. Note here that Z is positive up, and that's basically consistent everywhere through SimPEG. So anything below the surface is always Z negative. As I mentioned before, sometimes we want to add a few extra cells on either side just to make sure that before we start doing the padding, or that I guess the padding cells don't too strongly influence the physics. And so here we're just going to add a couple extra core cells onto that core domain, and then we'll add some padding cells. And this padding factor here, so for electromagnetic and electrical problems, we can actually add padding. These are nice equations for that. Seismic, for example, you don't typically want to be expanding or changing your cell sizes because you're dealing with a wave equation. But here we're dealing with diffusive equations. And so we can get away with expanding cells further away from our source. And so here I'm going to add 10 padding cells in X and in Z. So here, as I mentioned, for a tensor mesh, we can define 2 tensors, and defining basically the spacing in the X and in the Z directions. And so this here is specific to SimPEG, the way that we set this up. So the first part in X that we do, so we define the cell sizing, the number of padding cells. So this is defining the padding portion on the left-hand side of the mesh. And then the negative is a trick to basically say we want them expanding in the opposite direction. So I'll show you actually just what this looks like. So I'm going to show you a plot first, and then we'll come back to what was just printed there. So these are those padding cells. So when I said the negative flips that is we start with the widest cells at the very edge of the domain. And then we can see our core region here. We've got padding on this side, and we've got padding to depth. Some of the things that we've printed, so the total number of cells, this is going to be a big controlling factor on how expensive your computation is. So if this is hundreds of thousands of cells, it's going to be very expensive. On the order of thousands, we should be able to run this pretty quickly. Some of the other things we're worried about, as I mentioned, is the extent of the mesh. So making sure it goes sufficiently far beyond our survey. The minimum cell sizes, and then here we also show the maximum cell size. So those are the biggest padding cells. And so this beautiful printing here, this was a contribution by Dieter. So if you are enjoying that, I should give a shout out to him. Okay, so now we've got where we're actually going to run our computation. So let's actually set up and construct the forward simulation. So this is, the simulation is kept track of by a simulation object in SimPEG. So it contains everything that we need in order to compute fields and fluxes on a mesh. So we instantiate it with a mesh because that's our computational domain. And that also gives us all of the differential operators. The other thing that we're going to instantiate it with is something called a mapping. And so what this is in SimPEG, we've defined the maps module, which gives us a lot of flexibility for basically defining what our inversion model is. So we know that the DC resistivity equations, we need to be working with resistivity values on the mesh. But that's not necessarily what we want to invert for. So as I showed you earlier, resistivity can vary on several orders of magnitude. And so perhaps a more natural description is actually taking the logarithm of resistivity and inverting for the log resistivity. And so if we want to do that, then our inversion model are going to have values of log resistivity. And in order to get that to be something meaningful on our computational map or in our computational mesh, we need to take the exponential of it. And so that's what an exp map does. And so in the inversion, it's important that we have derivatives of all of these operations because that's going to be how we compute updates. And so the mappings module keeps track of both how do we translate from the set of parameters that we invert for to a meaningful physical property on the mesh, as well as all of the derivatives. And so once you start to get familiar with this mapping concept, it can actually be pretty powerful. So for example, we use this to also make sure in electromagnetic inversions that we don't invert for air cells, because we need to simulate the equations in the air, but we know where the topography is and we don't want to be inverting in the air. So we can choose the subset of cells that we care about in the inversion. You could also do things like defining parametric models. And so if I wanted to define a layered Earth model, and instead of inverting for resistivities in voxels, if I wanted to invert for a layer depth and resistivity of each of those layers, we could construct mappings to do that. But for now, we'll be working with the row map. Okay, so the other things that we need are a solver. And so in this case, we're going to use Paradiso, which is a bit of a faster solver for symmetric systems. And then the other thing that we're going to do is set this store j to true. So for smaller problems where we're not memory limited, the inversion is going to be a bit faster if we store the sensitivity matrix rather than computing it on the fly. Let me fix that. So for larger problems, you don't necessarily want to store the sensitivity because it is the size, it's a large dense matrix that is the number of model parameters by the number of data. So if you have lots of data and you have a big mesh, this can get very, very big. And so you may not actually be able to hold it in memory. And if not, that's fine because we have everything implemented to do matrix vector products. But if we aren't memory limited, in this case, we're not, it makes things faster. Cool. Okay, so here, as I mentioned, we're going to use this exp map so that we invert for log resistivity. So we provide the mesh, the mapping, the solver, the survey, and store j. And in this case, we're going to use the nodal discretization. There's also a cell-centered discretization. Within SimPEG, the naming convention is always so simulation and then the dimension. So in this case, we're doing a 2D forward simulation, and then where things are discretized. So in this case, on nodes. So I just want to show you some of the things that we have access to once we've created a simulation object. So we can do things like predict data. So dpred is going to predict data. We can get the fields. And so this is something kind of cool, and we'll explore that in the second notebook, where you can access the things that we solved for. So you can get potentials everywhere on the mesh. You can get electric fields and currents and charges. So we can actually start to visualize the physics using this fields object. We also have things like getting the derivatives, so computing the sensitivities and sensitivity vector products and such. And then you can see that row map that we set earlier, as well as the solver. So yeah, and there's a whole bunch of other things that we use when we actually solve, but the dpred, which predicts data, the fields, and then the make synthetic data methods are probably the ones you'd want to interact with most as a user. Okay, so now we've set up everything, and we should be able to go ahead now and run a forward simulation. So the first thing that we're going to do is we're just going to run a forward simulation over a half space. And this can be a good way to go ahead and check your mesh, because if we compute apparent resistivities over a half space, those should be the same as the true resistivities, because that equation is valid for a half space. So that's what we're going to do here. So we set up our model. You'll notice it's log resistivity, and it should be the same size as the number of cells in the mesh, because we've discretized resistivity on cell centers. So the vector that we input for forward simulations, inversions, etc., needs to be the same size as the number of mesh cells in this case. So we go ahead and run that. And now we can plot up the apparent resistivities. So here I've set this color bar limits to be what we used previously. And so we can see it looks like a half space, which is good. That's encouraging. If we comment that out, we can see there is a little bit of variability, but our true resistivity, the resistivity value that we input was 135, I believe. Let me check. Let's double check that again. So it is rho naught. Yeah, so 135, 136. So we can see it's centered around there. And we've got a variation of maybe 4 ohm meters in each direction. One thing that is insightful to look at, so we see, yes, there's some variability in the pseudo section, but then let's actually just look at the error in apparent resistivity. So I've computed the error. So we've got the apparent resistivity from the data that we just computed. And I'm just going to compare that to the expected half space resistivity and multiply it by 100. So this is a percent. And so in this case, we're within like 2.5% for these, which is sufficient. So the thing that you need to look for here is that we want to make sure that these errors are less than the errors that we set in the data. And so typically, we're looking at errors on the order of at least 5% in the data, or uncertainties in the data that are at least 5%. So as long as we are sufficiently below that value, then we should be in good shape, because the errors on the data are larger, and we're not trying to fit the data to within 2%, for example. Okay, so that's everything now. We've got everything set up to basically go ahead. Given a model, we can now predict data. So that's everything we need for the forward simulation. So next, we're going to go ahead and actually set up an inversion. And so as I talked about earlier, we're going to set this up as an optimization problem consisting of a data misfit term, which we're going to call phi d, and then a regularization term, phi m, that is weighted with a trade-off parameter beta. And so beta controls basically how important are the data misfit versus the regularization in the inversion. Now we're going to try and fit data. We want to reach what we call the target misfit. And this is controlled by the number of data. So if we've set appropriate uncertainties, then what we should be able to do is reach our target misfit, which is n divided by 2, because we define phi d as 1/2 of a weighted difference between our forward simulated data and our observed data. So here, the way the uncertainties come in, or the standard deviations come in, are through this WD matrix. So we're going to define this data misfit term. So we've got our WD matrix, and it's a diagonal matrix where we put 1 over the standard deviations along those diagonals. And so what this does is it then says, okay, if I've got a really small standard deviation, then this is going to be a big value. And so that means that if this difference, the difference between the simulated data and the observed data, if that's large, it's going to get amplified because we multiply it by something big. And so then the inversion is going to then try and minimize that. We want to try and reduce that. So that's the influence that has. If epsilon is really large, then the opposite happens, is that we basically reduce the influence of this difference. And so if you know that some regions or some data are noisy, then you can increase the standard deviations, and that'll reduce their influence in the inversion. So looking at this equation, what do we actually need in SimPEG to work with this? So this is all through the data misfit module, and we'll use an L2 data misfit because we're doing an L2 norm. And then it's instantiated with data, so the DC data. That's going to be what gives us our deobs, as well as the uncertainties. So the data object keeps track of both of those, and as well as a simulation. So a simulation then is what is going to be able to give us this term here. So we go ahead and create that. Okay, the next thing we're worried about is regularization. And so this is important because we're dealing with a problem that's ill-posed. And an easy way to sort of see this is if we think about a linear problem. And Matt wrote a really nice tutorial, which I've put a link here to, is that this matrix G has many more columns than rows. And so what that means is we got many more model parameters than we do data. And this is true, basically, I mean, this is true always, because even if we tried a parametric discretization or description of M, what we're doing is we're imposing a different set of assumptions, and we're imposing sort of a different style of regularization, is we're basically saying the Earth can only look like this. But in general, we have the general thing that we have is a continuous Earth. And so no matter how we break that up, this is always going to be an ill-posed problem. And so we have to impose some sort of assumptions to get back a reasonable result. And so in this case, the most standard and sort of approach where we're not imposing very strict assumptions, these are fairly standard assumptions, is using what we call a Tikhonov regularization. So it's composed of 3 terms for this 2D problem. If we had a 3D problem, we would add 1 more of these. And so this first term is called the smallness term. So we have this matrix WS, which we can use to weight the influence of these different model parameters. And we take a difference between M, our model, and then some reference model. And the reference model is important because here, if we are thinking, for example, about resistivity, and we're inverting for log resistivity, if you say, oh, I'm not going to use a reference model, I'll just set that to 0. What that actually means is that we are then actually trying to get M close to 0, right? We've set M ref to 0. But what that actually means is we're trying to bring M close to 1 ohm meter, which is actually pretty conductive and probably not geologically reasonable for a lot of the settings that we work in. So it's important to think through and set this reference model to something that you expect to see in the geology of the region that you're in. These next 2 terms are what we call smoothness terms. And so these are going to be looking at differences between model values in neighboring cells. So basically what we're trying to penalize with both of these is large gradients. We want to say, let's get out a smooth model, and we can interpret from there. Now the alpha values, as what we saw when we combined the objective function of the data misfit and the regularization with beta in between, these alpha values weight the relative importance of each of these terms in the regularization. And in Notebook 3, you'll get a chance to play around with those. So here, the way that we set this up is we use the regularization module in SimPEG, and we're going to use the Tikhonov regularization, which is of this form. So we need a mesh because that's going to be what we use to construct these differencing operators, the gradient operators, so that we know basically which cells are next to each other. And then we can set the alphas. So you'll see here I set alpha x and alpha y equals 1. Notice because we're doing a 2D simulation and inversion. In SimPEG, the naming of the dimensions is always x, y, z. And if we are only in 2 dimensions, then we just take the first 2 of those, which is x and y. So conceptually, and in all the code you saw me write above, I used z because we're thinking about it with depth. But when you actually set stuff up in 2D in SimPEG, just keep in mind that you need to be interacting with the y component as the second dimension. The other thing you notice here is I use a different value for alpha s. And that's because the values of alpha x and alpha z have a different dimension as compared to alpha s. So if we're taking a spatial derivative on these guys, there's a length scale that comes in. And so this is one mechanism for trying to rebalance that. And so again, in Notebook 3, you can play around with all those parameters. And you're welcome to play around with them here too. This is a good example to get a sense of how these parameters influence the results. But Notebook 3 has a synthetic example, so we know the true solution, whereas here we don't. Okay, so we've got basically the components of our objective function. So now we're going to set up an optimization. So here we're going to use inexact Gauss-Newton, and we set a maximum number of iterations. So you can set this as high as you want. But for exploring things, we want to make sure that we get to the end of an optimization run within a finite number of iterations. And then this controls the iterative solver under the hood. And again, that's something you can play with later on. Okay, so now that we've got the data misfit, regularization, and an optimization defined, we basically have everything that we need to come up with what we call like a statement of an inverse problem. Is we want to minimize our data misfit and regularization using this optimization routine. And so that's what the inverse problem module in SimPEG keeps track of. And it has all the capabilities to basically go in and evaluate the value of the total composite objective function, as well as its derivatives. Okay, so we've got a statement of an inverse problem, and now the last thing we need to do is basically say, how do we want to solve this? And so that is where the inversion module of SimPEG comes in. And so it takes the inverse problem that we just set up. So we've got data misfit, regularization, and optimization all in here. And then we take what's called a directives list. And so at this point, what directives are is they can orchestrate updates during the inversion. So for example, I talked about the value of beta, which controls the relative importance of phi m and phi d. We might want to try and estimate that. And so in order to do that, what we do, or one common approach, is to try and estimate what are the largest eigenvalues of basically the operators controlling each of these. So if we make a change, which of these terms is going to have a larger influence? And so that's what this beta estimate by eigenvalue does. The ratio here that we input allows you to basically dial up or dial down the importance of the regularization based on that estimate. So here, what I've basically said, if we set the ratio to 10, well, 1E0 is, what we set it to was 1, then I'm saying we should treat these as basically equal. If we set it to 10, that would basically say, let's try and have the influence of the regularization be 10 times larger than the data misfit initially. The beta schedule, and this is a fairly common approach in especially nonlinear inversions, is what we're going to do is we're actually going to update the value of beta over the course of the inversion. So rather than starting with a fixed beta and saying, let's try and fit our data that way, what we're going to do is we're going to say, okay, let's start with a high influence on the regularization. And at each iteration, as we get to try and fit a smooth model, because that's what the regularization is trying to do, we're going to try and we'll dial that back slowly as we start to introduce structure in the inversion. And so dialing back basically just means we're going to reduce the value of beta and allow the data misfit to have more influence in the inversion. So the cooling factor, it's going to reduce beta by a factor of 4 every 2 iterations is what that means. And then finally, we're going to use a target directive. And so this is just going to stop the inversion when we've reached the target misfit. If we didn't use this, it would run for 20 iterations because that's what we set as the maximum number of iterations in the optimization. All right, so we've got everything. Let's run it. So you'll see here, the first thing we noticed that popped up is we set the reference model to M naught. So as I showed you when we were talking about the regularization earlier, we want that reference model to be something geologically reasonable. And if you don't set it by default, SimPEG will set it to your initial model. But you can set them to be different things if you set the MREF property on the regularization. There's a few things you can see in the log. So we can see the beta value, the phi d, the phi m. You can see it only took us 3 iterations to converge to a solution, to reach the target misfit. So let's take a look at our predicted and recovered data. So I'm plotting 2 pseudo sections here. So the first one, we're going to look at what are the true observed data. And then the second plot, we look at what are the predicted data from the inversion. And so overall, that looks like a good fit. I mean, we're seeing similar features in both pseudo sections. And so it looks like we're doing a good job fitting the data. We can also look at the misfit. So this is looking at a normalized misfit. So what we do is we look at the difference between the predicted data and the observed data, and then normalize by the standard deviations. So if we fit all of the data within their standard deviation, these values would be close to magnitude 1. And so in this case, if we're seeing most values somewhere on the order of 1, then we're doing a good job fitting our data. And we also see there isn't anything that there's not too much structure coming into this data misfit pseudo section. So we're not it doesn't look like we're missing any major features in the data. Cool. Then here, I showed you those fault lines earlier in the slides. And so this is just going to load those up so that we can actually take a look and include them in our plots. So let's take a look at our inversion result. So you'll see here, I make sure to map the inversion result, right? Because M opt, we inverted for log resistivity, but now we want to look at resistivity. And so we can go ahead and we can actually see we're recovering some conductive structures like what we saw previously, a bit of a resistor here, resistive unit here. And so we can go ahead and load up the results from UBC, from the UBC inversion 20 years ago, which took a day. And we can compare those. And so overall, you can see we're seeing similar structures. The UBC one was run on a coarser mesh. So we've got 25 meter cells. These are 50 meter cells. But overall, from the eyeball norm, I think this is a pretty encouraging result, is to be able to see we've got these resistive features. We're getting our conductor here. This moderate resistor is showing up in both. And so that's pretty incredible, is that 2 inversions with 2 different codes, 20 years apart, we can get similar results. And so I see we're approaching, I guess, an hour and a half. So I think this is probably a good place to pause for about 10 minutes, give everyone a break, go top up your tea and coffee, and we can regroup in 10 minutes and maybe take some questions then. Right. Thanks, everyone. Let's get started again after our break. So just a quick recap is we've now gone through and we've inverted the DC resistivity from Century. We compared that to the UBC results, and to be very self-congratulatory, these are excellent results, and there's some nice agreement between the two of them. And also, Soggy Kang deserves a shout out for working through and doing the original inversion for both the DC and the IP data for Century with SimPEG. And so big thanks to Soggy for working through both of these. So next we'll move on to IP. So we'll go through the IP inversion, and then we'll pause and take time if there's questions that have surfaced before moving on to the next two notebooks, which we'll probably end up doing a short tour of given our timing, but that's all right. They'll be there for you to play with afterwards. Okay, so to remind folks what we're looking at, we're now going to be looking at chargeability. So basically, the ability for a material to act like a capacitor. So in this case, what we saw for Century is that we're expecting that the mineralized units should have a chargeable response. And so that's what we're going to be looking for. So as I mentioned before, we are using a linearized model for IP, where we're using the sensitivities from our DC inversion. And we're going to be inverting apparent chargeability data. So we're going to play a very similar game as to what we did before, where we loaded up our observed data file. So instead of this being a POT, it has now just been an IP, but then other than that is the same. And so we're using that same read DCIP data function that we wrote earlier. I'm just going to turn the verbosity off because we sort of now know what's going on with that. So this is just going to be that Python dictionary where we've got our A locations, B locations, M locations, N locations, observed data, and standard deviations. So the survey setup is very much identical to what we did in DC. The major thing that you will see that has changed is that instead of using the DC module, we now use the IP module. And in this case, we flag that our data are apparent chargeability data, because there's a few different ways to represent and quantify IP data. But in this case, we're working with apparent chargeability. If you're curious and are looking for more background on IP, I recommend both the GPG, which I provided a link to in the slides, and I believe should be linked in this notebook, as well as EMGSI. Okay, so we set up our IP receivers, set up our IP sources. So again, the only thing you're seeing that's changed is a DC now goes to an IP. And then we go ahead and can set up our survey as well as our data. And then similar to plotting the apparent resistivities that we saw in DC, we can also plot apparent chargeabilities. And so you saw this plot in the slides. And so we can see some interesting features in this pseudo section. Folks who are familiar with interpreting and working with both DC and IP data would recognize this pant leg structure here, which is often associated with some sort of compact target. It also looks like we're seeing something potentially chargeable at here. So there's a few interesting features in these data. And just mentioning, sorry, to remind folks where we saw this briefly was in the slide deck. And so it's just showing both the field data for these pseudos for this line. Okay, so we've got now our survey and our data set up. So we're going to define the IP simulation. And so very similar to what we did in DC, we are now just working with the IP module. We're still going to be using a nodal discretization. The main things you'll see that have changed or that are new is now we are inputting the resistivity model that we obtained from the DC resistivity inversion. And that's because we need this to construct those sensitivities. So we need this to construct basically what our forward operator is. The other thing is instead of working with a row map, we now work with an eta map because the physical property that we are working with is chargeability, which we use the symbol eta for. Okay, so that gives us everything we need now to simulate IP data. So now we can generate and predict IP data given a model. So again, we set up a data misfit term and a regularization term, again, using a Tikhonov inversion. In this case, we're not going to use an X map because chargeability tends to vary on a linear scale. Sorry, I should have included that plot from our slides. But we don't expect chargeability to vary by orders of magnitude. So in this case, taking an exponential is not an appropriate representation of that physical property. So in this case, we're going to end up using what we call an identity map. And so that just takes the identity, so it takes the values as is and uses those. But because we know that chargeability should not be negative, we're going to use a slightly different optimization than what we did for DC. So in this case, so for DC, we used a Gauss-Newton, an inexact Gauss-Newton with no bounds. In this case, we are going to impose bound constraints. So upper bound, we're not concerned about, but the lower bound does matter. So we've got a 0 lower bound. We should not obtain negative chargeabilities. And so this will project any values that potentially try and give us a negative step in the inversion back to 0. And then as before, we set up the inverse problem with the misfit, the regularization, and the optimization. So in this case, we're going to set a starting model. So instead of looking at apparent chargeability values like what we did in DC, we looked at apparent resistivity values for trying to estimate that starting model. What we're going to do here is it's pretty common in IP inversions to basically assume, let's assume that most of our background material and most of the rocks that we're working with are not chargeable. And so it should be small or close to 0. In this case, we don't want to set it exactly to 0 because that makes the optimization a bit challenging because that's exactly our lower bound. There's mechanisms if you do actually truly want to set this value to 0. There's ways that we can do that. And if folks are interested in that, feel free to ping on Slack. There's folks who can answer your questions and point you to things that you would need to consider, like appropriate preconditioners and such. And that all comes in with the directives. So it's an interesting point. But it is something that you can dive into in more detail with questions. But for now, we're just going to pick something that's sufficiently small. And we're going to use the same directives as what we did before. We're going to use the estimating a beta value. We're going to use a beta schedule. Here, we're going to cool every iteration because we're working with a linear problem. So we can cool every iteration because we've solved exactly at a given beta at each iteration. Okay, so then we can go ahead and run the inversion. And so in this case, we're seeing similar values, similar printouts as to what we saw before. The inversion converged in 4 iterations and took seconds per iteration rather than hours per iteration as per 20 years ago. So things have come a long ways. And then we can go ahead and actually look at the misfit. So let's see, have we done a good job fitting our data? So as we did for DC, we're looking at a normalized misfit. So we've got our predicted data minus our observed data, and then we normalize that by the standard deviations. So we want most of the values to be on the order of 1. They don't all need to be 1, but on the order of 1. So again, here we're seeing relatively small values. There doesn't seem to be any major structures that we saw in that initial pseudo section that are still coming through here. So that gives us a bit of confidence that we're doing a good job fitting our data. So we can take a look at the results. And so here, it's quite different than what we saw in the DC inversion, is we're getting 2 strong chargeable units, both fairly well aligned with where we expected to see mineralization. And again, we have the UBC inversion results, so we can go ahead and compare those. And so overall, again, we're seeing very nice agreement between the two different algorithms implemented in 2 different languages, run 20 years apart, is, I think, a pretty exciting result. And so, and again, here we're doing a good job delineating the extent of the mineralization. Okay, so with that takes us to replicating results from 20 years ago. And so I want to assign you some homework or some ideas that you can all play with after this tutorial. So here we only worked with one line of data at Sentry, but there are 6 lines in total. And so using the functions that we've built up here, so the file formats for those for those lines are the same as what we're working with here. The survey geometries are going to be a little different, but can you invert them all? And so if you take on this challenge, please just send along images in Slack. We'd be really curious to see what you folks get. And maybe down the line, we can actually compile these results and do a bit of a comparison. I think it'd be an interesting study. So yeah, please feel free to play with these and show us what you come up with. So with that, that takes us to the end of Notebook 1. We've inverted data from Sentry and are agreeing with these results here. So I want to pause for a moment and just see if there are any questions that come through on Slack that folks want to surface for us to discuss. And while we're doing that, we can go ahead and open up Notebook 2. And so Notebook 2 is going to be the DC forward simulation notebook, and it should look like this here. So we'll just pause for a moment, and I'm going to take a look at Slack. All right. Okay, I see lots of discussion happening, which is excellent. But I'm not necessarily gonna sort through all of those questions. It seems like most questions are being addressed by folks. So we can go ahead here and we'll get started with the DC forward simulation notebook. So in this notebook, what we're going to do is we're going to build up a synthetic model that uses the same survey geometry from that line in the Sentry survey and explore some things. So we're going to explore some things like mesh design and also show you how to set up and visualize aspects of the physics. And so if you're using this as a teaching tool, for example, if you want to explain some of the fundamentals of DC resistivity. Oh, I just see one question popping in. And so I will ask this. So Sagi's posted this from the Slack channel. So the question is it fine for the cooling factor to go negative? What would that actually mean? So in this case, you do not want a cooling factor to go negative. In fact, it doesn't make sense. It doesn't work for beta to be negative. We don't want to work with negative values when we're doing an optimization, when we're trying to minimize something, because what that would actually mean is we're effectively then trying to maximize a value of something. So if we put a negative beta, we would be actually trying to basically do the reverse of regularization, which isn't necessarily going to give us positive results. A follow-up to that is with respect to what happens if you were to increase beta. And so in that case, you could, but what that would be doing is you would then be increasing the influence of the regularization over the data misfit. And so effectively what that statement would be is you're then trying to effectively increase the assumptions that you're imposing at the cost of respecting the data. And so that's not necessarily something that you would want to do because the data are our source of truth. Our assumptions are things that we think we know about the setting, but we want the data to be the source of truth. But there are some settings where you might want to play around with those types of things, and you certainly could set beta that beta cooling factor to be less than 1 and see what happens, because that would simulate that effect of increasing beta. There's another question here that's come in. So how flexible is SimPEG if I wanted to find my own cost function, for example, in the inversion? This is a great question. And I think one of the things that I'm most excited about with seeing what folks can do with SimPEG is that it is very flexible, is that you can define, we've set up the objective functions to be very pluggable and composable. So for example, you can define a data misfit term that's actually composed of 2 data misfit terms, and that lets us do a joint inversion. So if we wanted to do a joint inversion between gravity and magnetic data, for example, you would then construct a data misfit for the gravity data, one for the magnetic data, and then add those together with potentially some weighting in between. So Thibaut Astic has been doing some really cool work in his PhD thesis looking at joint inversions. And so you should check out his thesis when it comes out, which should be soon. as well as some of the papers that he's written on that. Also, if you wanted to define a different norm, for example, so in the regularization, maybe you want to try and define compact norms. And so maybe something like try and mimicking an L1 norm. So we want to try and promote compact structures. That's something that you can do as well. And so Dom Fournier's done a lot of that work in his thesis as well. And so there's some papers out about doing that. And so those are two to look at and get some ideas from. But if you, for example, wanted to include a data misfit term that we don't have, so maybe you want to use a different norm on the data misfit, maybe we want an L1 norm on the data misfit, although we don't have that implemented, as long as you implement the ability for that object to evaluate itself, given a model, and compute derivatives of that. We need the first order derivative and an approximate second order derivative. Then you're good to go, and that can be plugged in directly. Perfect. Okay. And there's a few other questions I see coming in asking sort of about extensibility or different receiver types, different data types. So in general, we've tried to design a very modular framework. And so as long as, for example, if you wanted to define a receiver type for apparent resistivity in a DC inversion rather than potentials, that's something that you could do. What you would need to do is then basically the thing that we simulate in the physics is electric potentials. So then on your receiver, what you would need to do is simulate or compute the apparent resistivity, and then also include derivatives so that we can go derivatives of that operation so that we can run the optimization. So in general, we've tried to design things to be very modular and very extensible so that you can try out your new ideas and different data types and things like that. For reference, a good place to go to ask these sorts of questions, and if it's something you are unsure of is plugged into SimPEG, or if you're not sure where to go to implement things, if you go to SimPEG discourse, so simpeg.discourse.group, we have a community discourse channel. And so here you can come and ask questions. And I see there's a lot of questions we need to get to as a team, some folks asking some interesting questions. So feel free to come and post your questions or ideas here, and we can try and support you, and users can try and support each other as you try and implement new ideas. Perfect. Okay, so let's get started on Notebook 2. So here we're going to set up a synthetic example and simulate some physics. So we're going to do the same imports as what we did before. So nothing new here. And again, loading up the DC data. This is the same function as you saw before. If you were doing this in a project, I would recommend you actually create like a Python file. So this is something that you can import. But here, if you wanted a refresher or wanted to go in and poke around and change some of these values, you could certainly do that. So we read in those DC data, and now we're going to construct our source list again. So now we've gone from Python, where we've got our data in a dictionary, and now we're going into SimPEG. In this case, one thing I'm going to change is rather than working in the coordinate system of the survey, for the synthetic example, let's just work in a local coordinate system. So the center is 0, and that'll just simplify things like setting up the model. Okay, so what we're going to do now is we're going to explore some of those factors that I mentioned with respect to mesh design. So some of these things like looking at the number of cells per electrode spacing, number of core cells, how deep we extend that core domain, the padding factor, and the number of padding cells. So this function basically just wraps what we did previously in Python code by setting up the mesh, and just let's, by putting it in a function, we can easily just go and change and swap out these parameters. So we can see that when we build mesh, it's going to return a mesh, and then it returns those core domains. And I do that because it's nice to be able to just plot the core domains. And we can see here that this is basically the same mesh as what we work with this notebook. And the next what I'm going to do is I'm going to define a couple of functions. So I'm going to define one where we just run a forward simulation over a half space. So we can provide the mesh that we just created, the survey, a half space resistivity value, and then this NKY. And so what this is the DC problem that we're solving is actually, it's like a 2.5D simulation. And so to get the other dimension, the third dimension, which allows us to actually truly simulate like point sources in 2D, we use digital filters. And so the NKY is the number of digital filters. And so this basically, it's a parameter we can increase and decrease. If you decrease it, we're going to decrease accuracy, but also speed up computation, because each one of these is basically an independent computation that we then are going to integrate over. And then if you increase this, we should increase accuracy. So it's a parameter you can play around with and get a sense of here. And then finally, this is just plotting code. And so this is a mechanism for looking at the apparent resistivities given predicted data and the half space resistivity. Okay, so if we stitch that together, then now we can actually run basically a forward simulation in 3 lines of code, which is nice. So we can run the half space, we set a half space resistivity, compute some predicted data, and then plot apparent resistivities. And so here, these are the 2 plots that we were looking at before. Is we were looking at the pseudo section, where we know if we input a resistivity value of 100, we should be getting back basically a half space response at about 100 ohm meters. And then these are the error. This is the error. So this plot is looking at the apparent resistivity minus the true half space resistivity divided by the half space resistivity, and then times 100 to give us that value in a percentage. So by looking at this plot, we can then sort of mess around with simulation parameters and basically see what that does, see what changes our accuracy. So I stitched all of that together into a single function that basically takes all of those parameters so that we can build a little widget app around that. So here, this is basically just the code to define the widgets and give them nice names. One thing you'll notice, we use the continuous update is false. Because if you input a slide bar, for example, each time you slide over, it's going to run a new computation. And if these are relatively cheap computations, but they're not completely instantaneous. And so each computation is run only when you sort of stop interacting. Okay. So then before we start playing with this, I'm just going to pose a couple of questions. And so let's look at those 3 decision factors that we had before. Is if we change the number of cells per electrode spacing, padding, and then the core domain extent. Okay, so here we've got a few different slide bars. So these ones change the cell size. So this is right now, we can interpret this as this is 4 cells per 100 meters in the X direction. So that's exactly what we had done before, is we've got 4 cells per electrode, spacing. And then this is the same thing in the Z direction. These slide bars influence basically how many core cells do we add outside of the survey area. This parameter here controls the depth extent of our core domain. And so here, this is basically 1/3 of the maximum separation between our source and receiver electrodes. This controls the padding factor. So basically how quickly, when we looked at the mesh, sorry, I'm going to scroll up to the plot, basically how quickly those cells expand. So in this case, we used a factor of 1.3, but that's something that you can change. This changes the number of padding cells. This changes the half space resistivity on a log scale. And then this changes the number of digital filters. So here, let's go ahead and let's see what happens if we decrease the number of cells per electrode spacing. And so in this case, we should expect that if we decrease this value by too much, we should decrease accuracy because we're not able to simulate the physics as much. And you can see that starting to break down. So if we go only 1 cell per electrode spacing, we're off by probably on the order of 3-4% or something. Same thing now if we reduce the number in the Z direction. we can see this was fairly dramatic. If we go too coarse in the Z direction, we're now getting errors on the order of probably 8%. And this is unacceptable for an inversion where we want to be fitting data to within 5%. Okay, let's also take a look at the number of padding cells. So, one other thing I wanted to point out. Let's go back here. If I decrease this guy, we see that for the most part, it's really these short separations that are affected. So it's the near surface where we're doing a very poor job, because this is where when we have sources and receivers close together, that's where we're most sensitive to, is the near surface. And so if we're really doing a poor job sort of capturing the physics on these shorter length scales, we'll see it in the short electrode separations. Whereas now, if we start to mess with the padding, which is going to control if we are satisfying our boundary conditions or not. So let's go ahead and decrease this guy. Let's see what happens when we change the padding in the X direction. So you can see now the short spacings aren't as affected, but these further offsets now are. And so that is, that's because we're starting to violate boundary conditions, is that we have said that no currents can go through the boundaries, but the boundary doesn't extend far enough. And so we're getting currents out there. And so the solution is breaking down. And you can see even with 7 padding cells. So initially when I ran this, I tried with 6 or so. You can see that this isn't quite going to cut it if we want to get within 5% accuracy when we're trying to fit our data. So I encourage you to take a look at this and explore the rest of these parameters and see what kinds of meshes you can design, and see if you can build up sort of your understanding of where accuracy plays a role, where these parameters play a role in accuracy. The last one I'll point out is this NKY. So if we dial this down, the computation is going to get cheaper, but it will likely get less accurate. And so we can see where that starts to break down. And it's kind of happening all over the map. And that's because this is really changing how we're solving the physics. And so if we don't use enough filters, we're not actually capturing the physics well enough. Whereas if we are using, here we chose to use 11, and that's currently the default. We have fairly smooth errors with spacing. If we increase this a bit, we should be able to actually reduce these errors and increase accuracy. So you can see the axes changing, and it's a touch deceiving when they're all updating. But as we continue to increase this, we should see a bit of accuracy increase. And it seems like there's some accuracy increase in the middle regions here, but perhaps not as much of these more extreme offsets. So, but between sort of 18 and 11, we're noticing there's not a huge difference. So overall, we're doing a pretty good job with 11, and that will then speed up the computation because we don't need to do an evaluation for each of these filters. Okay, so the next thing I want to show is actually going ahead, and if we want to build up an example where we are exploring some forward simulations and want to explore the physics. And so this has been a really powerful teaching tool in explaining basically what are the fundamentals of DC resistivity, what sorts of things, what sorts of geologic settings does DC resistivity, is it not conducive to, and what sort of targets are we very sensitive to. So this, we're going to just define a simple model. We got a background, we have a resistive block and a conductive block, and then we just define the locations of those. So now what I want to do is I want to show you basically how you now put this geometry onto a mesh, because now that's where we need it to be able to evaluate the forward simulation. So I start out by creating a vector that's the same length as the number of cells, because we need a single resistivity value for every cell. And we'll just start by treating it all as the background. And then we're going to find the indices that correspond to each of the blocks. So in Discretize, the way that we can find these is through the grid properties on a mesh. So here you'll see some of the things that you have access to when we have a mesh. We have things like the area, we've got operators like averaging, we have operators like the cell gradient, for example. But the ones we're looking at here now are the grids. So grid CC is the grid for the cell center locations. You can also see we've got EX, so that's the edge, the X edges, the faces, the X faces, and N is for nodes. And so if you need to be trying to figure out where to put your physical properties, or if you wanted to, for example, look at the electric field, which we know is evaluated on X edges, and we're trying to really compare, do a code comparison or compare with an analytic, we want to compare the solution exactly where it's evaluated. So we might want to try and play around with the EX grid to find the locations that we care about. So again, as I mentioned, we use like the Fortran style of ordering. So each column corresponds to a given dimension. So in this case, if we look at mesh.grid tc.shape, we'll see it's 3900, which is the same as our number of cells by 2. And 2 is our number of dimensions. So the first dimension here is X. And then the second dimension here is what we're treating as Z. But again, if we actually wanted to access that grid, it would be called Y in discretize. So here we find the X locations and then find the locations that are greater than the minimum and smaller than the maximum. And then we do the same thing with Z. And then we can define rho at those indices to correspond to the resistive block. And then we just play the same game with the conductive block. So we can take a look at our model. Very simple model. So we've got our resistive block over here and our conductive block over here. In this case, we're going to use an identity map. We're not running an inversion, so we don't really need to worry about translating between log resistivity and resistivity. Let's just work in resistivity space. And then same, very similar setup as before. So we're going to run 2 forward simulations. We'll do the half space, and then we will do the block model. And this will allow us to basically compare how sensitive are we to the block, so we can take differences of with and without the block. So we can plot both pseudo sections. Notice that these are on very different scales. Apologies, I should have put them on the same scale. But this is basically identical to the background. And then here we see sort of 2 of these like pant leg style features in our pseudo section near the horizontal location where we put our blocks. So we definitely do see an impact in the data. So the next thing I want to do is we're going to go ahead and we're going to plot some of the physics. And so you'll notice here, sorry, I'll scroll up. When we actually computed the solution, rather than just doing the dpred or the make synthetic data like what we did in the previous notebook, here we actually access the fields object. And so in SimPEG, a fields object actually contains our solution everywhere on the mesh. When you're running an inversion, this is an intermediate step, is we only need our solution at the receiver locations to compare between our observed data and our predicted data. But if we want to explore the physics and try and get a sense of where the currents are going, where charges are being built up, then we want to actually save that solution and have access to it everywhere on the mesh. And so that's what the fields object does. Coming back to where things live, this is just a quick refresher. So physical properties live at cell centers. Potentials are at nodes. Electric fields and current density for this specific discretization live on edges. And so for plotting purposes, we want to average everything to cell centers. So there's 2 averaging operators we'll use. This av n2cc averages a scalar value from nodes to cell centers. So we'll use that to average the potentials to cell centers. And then E and J are vector quantities that live on edges. And so we want to use something that preserves the vector quantity. So here we use the average edge to cell center V. And so the V preserves the vector. So we'll get 3 values, an X, a Y, well, sorry. In a 3D mesh, you would get 3 values, an X, a Y, and a Z. In a 2D simulation, we'll just get the 2 components. So that's all this code is doing. And then we also include some plotting code. So you'll see some things in here, like I set different color bars. It's nice to sort of see charges on red, blue, but this isn't really anything too involved. It's just plotting code. So we'll go ahead and let's just take a look. And let's, for example, let's look at the secondary potential for source 15. And so you can see some interesting features. Actually, let's maybe start. So let's so if we look at the primary, this is the background. So just the half space model. You can see most of the action is happening near the sources. If we look at the total, which is going to be with the blocks, don't see much different. But if we look now at the secondary, it's the difference between those two. And so rather than having to type this every time, what we've done is I've just assembled this into a little widget. But this is going to be the only plot that updates. And so we can look at the model on a linear or a log scale. What I've been showing you before is on a log scale. So that looks more familiar with the previous plot in the notebook. And so let's go ahead and actually kind of just step through what's happening in an experiment. So I guess this isn't showing up very well, but the source locations, if I zoom way in, sorry, I'll fix this later on. The source electrodes are here and here, and you'll be able to see it when I turn on the current. So here's our model. Let's go ahead and actually look at what happens when we turn on the source. So here we're going to look at the source electric or source current density. And this is on a log scale. And so in this case, sorry, the white space here, this is a mistake I made in the plotting code above. I'll also update that. I should have extended it further, but it's just an artifact of plotting. So you can see here, we can tell which one is the positive electrode and which one's the negative electrode. So you can see the arrows are going this way. So we've got our positive electrode and our negative electrode, return electrode. You can sort of see it looks like currents are being diverted a bit around here and maybe perhaps preferentially flowing here. You can see that bend. So that gives us an indication we got something conductive here. And so what happens when we flow current and then it crosses boundaries between units of different conductivities, we build up charges. And so in this case, I'm going to flip over to the charge density. But before I do that, I want you to build up a picture of what do you think should be happening if we've got, so for example, we've got currents flowing around this guy, currents going this way, currents preferentially flowing into this target. Let's take a look. So I should do this on a linear scale. I stole my punchline. So we want to look at charge density on a linear scale. And so basically right now we see that the main charges in the system are due to where we actually have our current electrodes. It's a big plus right next to the positive electrode and a big minus near the negative electrode. But if we actually want to look at the influence of the blocks, we can look at the secondary charges. And so we see some interesting buildup of charges on the, this was the resistive block, and this is the conductive block. And so one of the things that would be interesting, and I challenge folks on Slack to actually play with this model, explore some of these physical responses, and let's see if we can actually build up an understanding of what's going on. So for example, let's start here. Why do we see a positive charge buildup on this interface? If we come back to the currents, and now we're looking at, let's look at total currents on a log scale. It's a little easier to see what's going on. Okay, so that the location of the block is right around here. And so we see we have currents flowing from what is a conductive block into a more resistive background. And so basically we've got charges that are going through a conductor. They hit something resistive. So you can almost think about them sort of like getting stuck there. And so that is what gives us this positive charge buildup on this interface here, is when we cross from conductive to resistive, we get a positive charge buildup. So one of the things that I think is constructive to explore and really trying to understand the DC resistivity surveys and also some of its limitations is what happens if we add a layer above the blocks. So let's say define a layer between Z is minus 50 and minus 100 and start with something resistive. Where do you see the currents and charges building up? Do you think we still see the blocks in the data? And then try with a conductive layer. What changes? And so if you want to post some of those images on Slack, then we'd be really curious to see what you come up with. And also come up with some creative models. If you've got an interesting geology or an interesting setting that you're working in, and you've got a conceptual model of that, see if you can plug it in and see what you see. So feel free to send us images and screenshots on Slack with your short explanations of what you think is going on. And we're happy to chat through that with you. And so here we'll pause for a moment before switching over to notebook number 3. And if there's any questions that folks have, feel free to send those through. And the SimPEG team on Slack will flag them for me. And in a brief interlude, while we wait for any questions that come through, I want to point folks to the SimPEG website. So we've got the website is simpeg.xyz. This is our main landing page. There's links with just a bit of a description of what SimPEG is, walk through some of the components. There's links for installing, joining the discourse. There's a video. So Rowan and Sagi gave a talk at SciPy a few years ago that provides a nice overview. And then lots of links for getting connected. The other links that we have here are for the documentation. So the link is docs.simpeg.xyz. And so here you can find some instructions for getting up and running. There's a whole suite of tutorials. So Devin Cowan deserves a lot of credit for bringing these tutorials and getting them into shape so that you can walk through. And for example, if you want to see how to forward simulate or invert magnetic data, for example, there's tutorials on how to do that. So referring back to that previous question about different norms, for example. So here's one where we show a sparse norm inversion with magnetic data. So you're welcome to check those out. Okay, I don't see any questions coming through at this point, so let's get going on notebook 3. Okay, and so, sorry, I scrolled right to the bottom of this one when I was checking that things were working, so we'll scroll up to the top. So in this one, we're going to use a synthetic example, so the same or a similar block model as to what we used before, to explore some aspects of inversion. So we'll explore setting uncertainties and show you how to do that. Adjust some of the regularization parameters and look at trade-off parameter, look at setting a reference model, and a lot of these choices and seeing what impact that they make in the inversion. Okay, so let's start with, again, the imports that we've done before. And we'll go ahead and we'll load up the DC data. So this is, again, the function that we saw before. Again, if you were actually doing this as a library, you'd want this to be something that you store in a Python file. But for completeness, and if you need a refresher, it's all there. And then we set up the survey again. So we've done all this now a couple of times. We build our mesh. And so this is just the same function that we used in notebook 2. And so we can go ahead and plot that and take a look. So this is the same mesh we've been using throughout. And then we're going to use the same model geometry as what we did before. So we've got our block model. I changed the color scheme on you between notebook 2 and 3. Just wanted this to be a bit more in line with what we were looking at when we were looking at the century data. Okay, so we start by defining our true model. And in this case, we're going back to working in log resistivity because now we're running inversions again, and we want to work with the log resistivity in the inversion so that it's strictly positive and it can vary logarithmically. And that's the space in which we search for a solution. So now we're going to generate some synthetic data. So again, we use this XMAP, this nodal simulation, and we're going to store the sensitivity so that the inversion is a bit faster. Now, to generate the data, we're going to use this make synthetic data method. And so what you can do with make synthetic data is it's actually going to return us a data object. So that's the same thing that we were working with in the first inversion to capture everything about our field data. So it's going to have the survey in there, the observed data, as well as uncertainties. And we'll assign those uncertainties afterwards. In this case, we're going to add some noise to our data. And so we're going to add 5% noise in this case. That's the default. If you wanted to change that, we can look at making synthetic data. So we can look at the documentation there. And you can see that you would change the relative error term here in the make synthetic data function. So if we wanted to add 10% noise, you would just add 0.1. Okay, so we generate our data, and then we can plot a pseudo section of those data. So it's similar to what we saw in the previous notebook, but there is a bit more noise and jitter to it. And that's because we added them. So as a quick refresher, this is what we're doing to solve the inverse problem, is we're setting up an optimization problem. We define a data misfit, a regularization, and a trade-off parameter between the two. We're going to run the inversion until we hit this target misfit, and then potentially include some bound constraints. In this case, we're not including those, but for the general case, we could. And then again, here's what those terms look like, is we've got our data misfit term, where the uncertainties are captured in this WD matrix, and then our regularization term, where these WX and WZ are basically approximating derivatives, as we want to enforce now that there are not large gradients between adjacent model cells. The WS in a typical case could be an identity matrix. But also if you are doing, for example, a potential fields inversion, you could use depth weighting there or sensitivity weighting. So there's a bit of flexibility with what you do with this. And then the parameters that we'll also focus in on are these alpha S, alpha X, and alpha Z, which influence how important each of these smallness and smoothness terms are in the inversion. So the first thing we're going to look at is focusing in on the data misfit term and assigning uncertainties. In the first notebook, they were given to us, but that's not always the case. And so in this case, what you want to do is we're going to look at the histogram of our synthetic data. Typically, when we assign noise or standard deviations, we think about it in two parts. So we think about it having a relative error. So that's like a percent error. And so in this case, that's going to multiply the absolute value of our observed data. And then we talk about also a noise floor. And so the noise floor effectively quantifies what is close enough to zero. And so it's important to include this when we have data that has both positive and negative values, which we do in this case. In DC, we do. Because we don't necessarily want to fit, if we have a small datum, if it's close to zero, we're not necessarily concerned about fitting that to 10 orders of magnitude. So the noise floor is what basically says this value is close enough to zero. And so a good way to try and assign that is by looking at a histogram of your data, because that gives you a sense of what is small. So in this case, if we look at the log of the absolute value of our observed data, we see a distribution like this. So we've got basically 2.5 orders of magnitude between our smallest values and our largest values. And looking at this, so we see our smallest values around log of 10 to the negative 3.5. So something like 10 to the negative 4 is small for these data, and will ask us to fit all of these data. If, for example, you didn't necessarily trust your smallest potential values, which is sometimes the case, sometimes we don't necessarily trust the really small values because they're very long offsets and we're not necessarily sure the instruments are always sensitive to that, then you might want to define a slightly larger floor, and then we wouldn't be fitting those data. And then there's also a relative error. So sort of how much background noise do you assume? 5% is what we'll do in this case, but that's again something that you can play around with. And so just to show you basically where our noise floor lands is here. So that is fairly small compared to our data. So now that we've made these decisions, so we've decided what our relative error and noise floor are, we want to assign those to the data. So we can assign those by setting the relative error and the noise floor properties of our data object. And then what I want to show you is that actually, so within SimPEG, what we use to construct the WD matrix is the standard deviation vector. And that's constructed exactly as I showed you before, where we've got the relative error times the absolute value of the observed data plus a noise floor. And so this little statement here is just to show you that that is the case, is that these are all close. If we evaluate the uncertainty like this, that's exactly what is going on when we ask for the standard deviation from the synthetic data object. This next plot is not necessarily super intuitive, but I just wanted to show you to give you a sense of how the percent error and noise floor influence different parts of the data. So what I've done is sorted all the data by magnitude. So the x-axis here isn't super meaningful other than larger numbers are bigger amplitude data than smaller numbers. And then this blue shadow is basically what the uncertainty envelope is around those data. And so here, when we're looking at large data, it's the percent error that, or the percent standard deviation that controls how wide that is. Whereas when we look at smaller data, it's the noise floor, so the 10 to the negative 4 that controls basically how large that uncertainty is. So just giving you a sense of, based on the magnitude of the data, which of those terms is influencing things. All right, so next I'm going to create a couple of functions that set up the inverse problem for us in a way where it's going to be easy to go ahead and change all of these parameters. So this is very similar to what we did in the first notebook. Is that this function here is going to be responsible for constructing the inverse problem. And so that's the object that contains the data misfit, the regularization, and the optimization. The parameters that can go into that we might want to change. So on the data misfit, we can mess with the noise floor and the relative error, so changing our standard deviations. In the regularization, we can change those alpha parameters as well as the reference model. And then in the optimization, there's two parameters we can change: the maximum number of iterations and then the maximum number of solves. And this can basically act like a bit of a regularization term, as well as the CG solves are somewhat smooth. So if we do less CG solves, the results that we get are a bit smoother. So that's something you can play around with it. It won't be the focus of our next examples. So here we set up the data misfit. So if we've changed those relative error and noise floor, then we update them here. And then we assemble that data misfit. Same thing with the regularization. This is what you saw before. The only thing to know here is that our reference model needs to be the same size as our number of cells in the mesh, because that's the number of parameters that we are inverting for. So in this case, I want to perhaps just change a scalar value for the reference model, but when I input that and instantiate the regularization, it needs to be a vector that is the same size as the number of model parameters. And then we do an optimization, set that up, and assemble in the inverse problem. One thing I wanted to show you, and this is a bit more of an advanced step, and so I'm not going to spend time dwelling on it, but I wanted to give you a sense of how the directives actually operate. And so here what I'm going to do is I'm actually creating a new directive class. And so when folks were asking about, sort of extending SimPEG and exploring your own ideas, this is one example of that. And so here I inherit the base directive, and then there's two methods that I'm going to create. So what I want to do in this one is I want to just save information that I might want to plot after the inversion runs. And so what we're going to do is there's two methods we define. There's the initialize method, and this is called when we first start running an inversion. So when we did that inv.run of a model, this is called before we do any sort of computation about what predicted data are or anything like that. And so, for example, if in the like estimate beta directive, this is where we estimate an initial beta and assign that in the inverse problem. The end iter is run at the end of every iteration. And so, for example, the target misfit is evaluated then. So once we run to the end of an iteration, the target misfit will just check and say like, hey, did we reach our target misfit? If yes, let's stop the inversion. If not, keep going. The beta cooling is also evaluated at the end of an iteration. And so it's going to check, should I be cooling beta at this iteration? If so, it will reduce the value of beta, and then you keep going. In this one, when I initialize, I just create an empty dictionary where we're going to just store some interesting inversion results. So we'll store things like the iteration, maybe the phi m, phi d values, the predicted data, the model, etc. And at the end of each iteration, I'm just going to append those values. So that's all this code is doing, is it's just saying, look at the current value and let's store it in this dictionary. So there are utilities for doing these sorts of things in SimPEG, and also for saving it to output files and such. And so in general, before you start implementing your own sort of custom piece, it's worth taking a look at what's there. But just wanted to show in case you do want to. So in addition to the saving results directive, we're going to use the three others that we used before. So we'll estimate an initial beta. We'll use a beta schedule to cool the value of beta. And then we will use a target misfit. And so one thing to notice with the target misfit, and we didn't talk about this in the previous notebook, but I'll just highlight it here. So one of the things you can do, so we know phi d star should be the number of data divided by 2. But for example, you can include a chi factor that scales that. And so if you multiplied this by a factor of 2, then we would stop when phi d equals n. Or if you reduce this, then we would try and fit the data. We would try and reduce the value of phi d more. But by default, that's 1. But I introduced that here as something that you can play around with if you want to explore that. So this function is going to take an inverse problem and set up an inversion. So there's parameters for the estimating the initial beta. There's the option to cool beta or not. So if you want to play around with a fixed beta, you can do that. We can change the beta cooling factor and the rate. So right now, what this says is we're going to cool beta. We'll reduce beta by a factor of 2. So if beta was 10 at the first iteration, at the end of the second iteration, what did I say? It was 10. So if beta was 10 at the first iteration, at the end of that iteration, we reduce it to 5. And then finally, we set, are we going to use the target misfit as a stopping criteria or not? And in some of the first examples I'm going to show you, we're not going to use that because I want to show you what happens when we overfit data. So this function is just doing exactly what we've done before. We set up those directives. We assemble a directive list. If we're going to use the target, we add that to the list. If we're going to cool beta, we add it to the list. And now we then just have an inversion. And I also ask it to return the target and the save because we're going to pull parameters and extract parameters from those afterwards. Okay, so let's go ahead and run some inversions. Just keeping track of time. Okay, so we'll start with a row knot that is equal to the background. So that's our starting model. And then in this case, we set up those functions. For now, I'm just using the default values, like what we set earlier, for both. And we're going to explore some of the things that happen here. So I set my initial model. Remember, we're inverting for log resistivity. So I'm going to take the log and then multiply by the number of cells because we're inverting in every cell. And then we'll run that inversion. And then here, this is new, is that inversion log, which is that that save inversion directive. So here, when we created the inversion, we got back an inversion object, the target misfit object, and the inversion log, which contains that dictionary of our results. Okay, so we'll go ahead and run that. And you'll notice in this case, I said, let's not use the target misfit. So we're going to run this inversion for 20 iterations. So it's just going to chug along for 20 iterations, irrespective of if we reach the target misfit or not. So some things you can see is we can see that we started with a large beta here, and it's decreasing every iteration because that's what we told it to do, by a factor of 2. Phi d is decreasing with iteration. That's a good thing. That means we're doing a better job at each iteration of fitting our data. And so you can see, we started at 10 to the 3, and we're now reduced down to something that is on the order of 1. And phi m does the opposite. Phi m starts low and increases because we're introducing structure. And by introducing structure, that means we are introducing gradients and we're introducing values that are different than the reference model. So now what I'm going to do, now that we've finished our inversion, run for 20 iterations, I'm just defining a few functions that are going to be useful for plotting and analyzing the results. So the normalized misfit, like what we looked at before, gives us a sense of how well we're fitting our data. And you can see these values are pretty small because we ran for 20 iterations. So this is smaller than what we've seen perhaps in other inversions. It looks like we've gone past the target misfit. Then the next thing I'm going to do is now define some functions where we're actually looking at those inversion results, and we're going to plot things like phi d, phi m, etc. And so in this case, we can plot the inversion results either as a function of iteration or as a function of beta, and look at those. We can plot the misfit and regularization, and we can plot the regularization components, so the smallness, smoothness, and such, as well as the Tikhonov curve. So rather than explaining all the code to you, I'm just going to show you the images, and then we can revisit them. So we have these functions. And so the first thing I'm going to do, I've created 3 plots. So in the first one, we'll plot beta as a function of iteration. The second one, we'll plot the misfit and regularization. And then the third one, we'll plot the regularization components. Okay. So we can see we started off with a large beta, and we reduced beta by a factor of 2 every iteration. So that's what we can see in this plot. This plot here is showing us now phi d, which is in orange, so our data misfit, phi m, which is in green. You'll see those are on different axes. So phi d is on this axis here, phi m is on this axis here, because they're on different scales and they represent different things. But beta is, again, what relates them. And then here, the black line is the target misfit. I also included a black dash dot line if you want to play around with this chi factor. And if you do that, you'll see that these lines separate and go to different places. But for now, we're treating them as the same. So you can see after, 1, 2, 3, 4, 5, 6 iterations, it looks like we fit our data. But here we continue on and we can look at those model results. And then here, this is looking at the smallness and the smoothness terms and seeing their influence. And I've included the alpha values in that evaluation. So you can see here, it looks like the smallness term increased the most. And so we're getting structure increased. And it looks like overall the smoothness it's smoother in Z than it is in X because these values are larger. Another useful way to actually look at the progress of an inversion is through a Tikhonov curve. And so what we're doing here is we plot phi d against phi m. And so when we start the inversion, we start with a very large phi d and a very small phi m because we started with our reference model and true model identical. So phi m should be 0 exactly. But then as the inversion progresses, we decrease the value of phi d while increasing the value of phi m. And so there's a number of criteria folks use to pick and choose what is your best inversion model. The target misfit criteria would then be what's the first inversion result below our target misfit. Other strategies try and look at where's the elbow of this curve, and we pick that model. And so you can play around with these. So what I'm going to do next is just define a couple more functions that are going to allow us to sort of interactively explore our inversion results. So in this case, what we're doing is we're going to plot, there's three things we're plotting. We've got the Tikhonov curve, we've got our normalized misfit, and we've got our resistivity model. So at the initial iteration, we really don't see much here. Our misfit basically looks like our data plot because we haven't fit anything yet. But as we scroll through and we go from iteration to iteration, you start to see a bit of structure introduced. So we're seeing this conductor starting to show up. And you can see here when we actually start to hit our target misfit. So it looks like this iteration, perhaps we've gotten close to our target misfit. So we can see both blocks starting to show up. Now, if we continue on, the targets get stronger. So perhaps if you wanted an inversion result more like this, and if we were evaluating our noise model and things like that, maybe we would reevaluate our noise model if we think that this is true and our target misfit was set too high. But if you keep going along, what we can actually start to see is eventually there's going to be some extra structure that starts to get introduced. So we see some interesting features happening here. And so what this is starting to show us is that our inversion is actually basically starting to go in and fit some of the noise. And so even though we're pushing our data misfit really hard, we're really trying to respect the data, that's not always something that you want to be doing, because here we're introducing more structure than what is actually geologically reasonable in this case. And so that's why choosing an appropriate dropping criteria is an important thing to do. Okay, so we're 10 minutes out. So I want to just show you a couple more things that you can look at. One thing that I did is I copied that little app code right here immediately below the inversion so that you can just run the inversion and explore. Note that this is sort of one of the features, but it also can be a drawback if you forget about these things with the notebook, is that this is run out of order, right? I need all of these functions in order for this to work. So just remember, if you comment this out, or if you uncomment this and make it live, and then you shut down this notebook, and 2 weeks later you want to play around with it again, you first need to run these cells below. So there's a few different things you can go ahead and play with. We can look at the alpha values. We can look at the influence of the noise floor and the reference model. So the first ones I want to focus in on, I'm just going to reduce the maximum number of iterations so we can save ourselves a little bit of time. But let's see what happens if I really increase alpha Z. Let's say I know that I'm expecting vertical structures, a pipe-like structure, and I just want alpha Z I want to really smooth things in the Z direction. What happens? So we can go ahead and rerun that and see what happens, and we can explore those results. So again, we started at the same phi d. We started with the same model, so that should be the case. Again, phi m is 0. And now we can go ahead and look at these results. And so in this case, as we scroll through and look at our updates as a function of iteration, we can already see some very vertical structures being introduced. This one's a little more subtle. The resistor is a bit more subtle, but this conductor, we're really seeing something come through quite vertical. And if we look here, this is our first iteration below the target misfit, we're actually seeing some pretty strange structures. I mean, yes, it does look like this is one coherent unit, but we're starting to see a little bit of striping. And so, yeah, so a slightly unrealistic geologic structures, but it is fitting the data. We fit the data, and this model respects the data. But for example, if you were expecting some smoothness in a given direction, you can change these values, maybe a factor of 2 up to a factor of 5, 10, can still give you reasonable results. So I encourage you to play around with these values and see sort of what structures can you get out that are geologically reasonable, by playing around with these parameters, but still giving you to just get if we set these guys. One other thing I want to show you, because I think this is a useful understanding of basically how sensitive your data are, is what happens if we change the reference and the starting model. So let's change the resistivity, our starting and reference resistivity, from the background model, which we know is the true background, and let's make it twice as conductive. So we've made this more conductive. So we've reduced the resistivity by a factor of 2. So let's go ahead and run an inversion. We'll again stay at 10 iterations, and we can see what happens. So in this case, when changing the reference model like this is a tool that's often used to estimate the depth of investigation of an inversion result, is running inversions with different starting and reference models. And I'll show you why. Is because here, if we then look at those results in our app, so we'll scroll through. So you can see that the color's different here. It's because we started with a more conductive background. And so as we go through iterations, we can see we're starting to actually get closer to the true background resistivity near the surface. And we're starting to then see that resistive block and conductive block come through. And then it looks like we're starting to fit the data around here or here. You could switch between those two inversion results fairly readily. But we see, so perhaps sort of like this sphere here, hemisphere of data, we're starting to get the right background model. But outside of that, we're basically controlled by what we started with. And the regularization really is driving what we see there. Even if we continue sort of pushing the inversion as hard as we can, these regions don't change. And so what that tells you is that we don't really have any data that are telling us much about this region. This region here is really controlled by the regularization. And so our sensitivity, the sensitivity of our data does not extend that far. And so when folks talk about a depth of investigation, this is one mechanism that you can use to try and understand which regions of the mesh and which regions of the domain do we actually have data that can support model changes and changes to the resistivity there. And so I realize we are coming up on the hour. And so what I want to leave you with this inversion and this example is a few more ideas of things that you can share. So as in the previous example, in previous notebook, what happens if you introduce a resistive layer, a conductive layer? How does that change our ability to resolve those blocks? And then get creative. Let's see if you can build up an interesting model and try and stump some folks, and try and see how hard you can, see how well you can recover it, and see what things are really challenging to recover in a DC resistivity inversion. So please send us your interesting images and ideas on Slack, and we'd be happy to follow up and continue the conversation there. And so with that, I will say thank you to everyone. Been a pleasure being with you today, and I hope you've learned some things. I just wanted to put up the resources slide again. So there's a few links in the GeoSci site for learning both about sort of the fundamentals of geophysical surveys, as well as some aspects of inversion. And then again, to end with a shout out to everyone. I had the pleasure of speaking with you all today, but this certainly would not have happened without an incredible team of people who've dedicated a lot of effort to SimPEG, and also specifically to this tutorial. So thanks to everyone here.